New megaprojects are breaking ground in 2026 and reshaping the future. Giant infrastructures from coast to coast are rising, from ultra-modern transit networks to record-breaking energy installations. In this documentary, we dive into the unprecedented engineering challenges and game-changing technologies driving these colossal builds. At the center of North Texas's expanding regional rail network, the DART Silver Line stands as one of the most complex transportation megaprojects under construction in the Dallas region in 2026. Unlike traditional light rail lines, the Silver Line is being delivered as a commuter-style corridor designed to connect suburban employment centers, major airports, and existing rail systems across multiple cities in Collin, Dallas, and Tarrant counties. The Silver Line is a roughly 26-mile east-west rail corridor stretching from Shiloh Road in Plano to DFW Airport North Station. It repurposes and upgrades an existing freight rail right-of-way, requiring extensive coordination between passenger rail construction and ongoing freight operations. This shared corridor condition defines much of the construction activity occurring in 2026, making the project significantly more complex than greenfield rail lines. By 2026, the Silver Line is firmly in its peak construction phase. Track installation and rehabilitation are ongoing across multiple segments, including full replacement of rail, ties, ballast, and drainage systems to meet passenger rail standards. In several areas, parallel tracks are being added or extended to allow freight and passenger trains to operate simultaneously without service conflicts. These works require nighttime construction windows and precise scheduling to minimize disruption. Station construction is a major focus during 2026. All planned stations serving Plano, Addison, Carrollton, Capel, and DFW Airport are in various stages of vertical construction. Platform structures, canopies, elevators, stairways, and pedestrian bridges are being built concurrently at different sites. In 2026, crews are installing structural steel, pouring elevated platforms, and beginning architectural finishes at stations that reached foundation completion in earlier years. Grade crossing reconstruction defines another major category of 2026 construction. Dozens of roadway crossings along the corridor are being rebuilt or upgraded with new signaling systems, gates, medians, and roadway geometry. Some crossings are being closed or consolidated entirely to improve safety and reduce long-term maintenance. These works require coordination with local municipalities and involve phased traffic shifts that extend throughout the year. Bridge and structure work continues through 2026 at multiple locations. Existing rail bridges are being widened, reinforced, or replaced to support increased rail traffic and modern load requirements. In flood-prone areas, embankments and culverts are being rebuilt to improve resilience against extreme weather events. These civil works represent some of the most capital-intensive portions of the project. Systems installation accelerates significantly during 2026. Crews are deploying signaling and train control systems designed for higher speed regional rail service. This includes centralized traffic control infrastructure, communication systems, and safety monitoring equipment. Fiber optic networks are being installed along the corridor to support real-time operations, dispatching, and passenger information systems. From a timeline perspective, 2026 is a transition year between heavy civil construction and operational readiness. While earthwork and major structures dominate early phases of the project, 2026 sees a shift towards systems integration, station completion, and corridor-wide testing preparation. Track work and signaling installation continue into 2027, followed by extensive testing and certification. Revenue service is not expected to begin in 2026. Instead, late 2026 and 2027 are dedicated to system testing, operator training, safety certification, and coordination with freight rail partners. Full passenger service is anticipated after completion of these phases, with opening targeted in the latter part of the decade, contingent on testing and regulatory approval timelines. Within the broader context of Dallas megaprojects under construction in 2026, the DART Silver Line is distinct for its regional impact rather than visual prominence. It directly connects major job centers, suburban cities, and DFW Airport without requiring transfers through downtown Dallas. Its construction reshapes an existing rail corridor into a modern passenger system, expanding mobility options across one of the fastest-growing metropolitan regions in the United States.
On the eastern edge of San Francisco, where rusted cranes once loomed over a forgotten stretch of shipyard, the Pier 70 redevelopment is one of the city's most ambitious megaprojects currently under construction in 2026. This historic industrial zone, nestled between the Dogpatch neighborhood and the bay, is being transformed into a vibrant waterfront community, one that blends housing, jobs, public parks, and restored heritage structures into a single cohesive district. The construction underway this year marks the most active phase of the project to date, with key milestones approaching as the site charges toward completion in the early 2030s. As of 2026, multiple parcels across Pier 70 are under simultaneous construction. Residential towers are climbing skyward, with the first phase of housing expected to be completed by 2027. These buildings will deliver nearly 1,100 homes in their initial stage, 25% of which are reserved as affordable housing. Construction crews are also working on major infrastructure upgrades across the site, including new streets, transit corridors, pedestrian paths, and shoreline protections to guard against sea level rise. The heart of the mega project is its connection to the past. Pier 70's redevelopment in 2026 doesn't erase its history, it builds on it. Several historic buildings are being restored and repurposed. These include old machine shops and steel foundries that once supported the shipbuilding industry. In 2026, many of these structures are undergoing seismic retrofitting and interior renovations to be converted into arts venues, retail hubs, and office space for design and tech firms. The goal is to preserve the gritty industrial character of the site while making it usable and vibrant for a 21st century city. Public space is a major focus of the construction effort in 2026. Over 9 acres of parks and waterfront access points are being built across the site. The highlight will be the large central green, an expansive park framed by restored industrial sheds and framed by views of the bay. As of this year, grading, drainage, and landscaping are underway, with full park openings projected for 2028. These open spaces are being built to double as climate infrastructure, designed to absorb stormwater, manage heat, and protect the site from flooding. In addition to housing and public amenities, the commercial component of Pier 70 is actively rising. Office buildings tailored to life sciences, technology, and creative industries are under construction now, with tenants expected to begin moving in by 2027-2028. These buildings are designed with flexibility in mind, featuring adaptive floor plans, outdoor terraces, and energy-efficient systems. Construction in 2026 is focused on delivering the first phase of these workspaces, helping to establish Pier 70 as an employment hub linked directly to the city's evolving economic base. The location is also a key asset. In 2026, construction crews are coordinating with transit agencies to enhance connections between Pier 70 and the rest of the city. Muni lines, bike lanes, and pedestrian links to the nearby Dogpatch neighborhood are all part of the ongoing infrastructure work. There's also future planning underway to accommodate ferry service, which would further connect the development to the regional transit network. When fully completed in the early 2030s, the Pier 70 redevelopment will deliver over 2,000 housing units, 2 million square feet of office and commercial space, 9 acres of parks, and over 300,000 square feet of retail, cultural, and community uses. But in 2026, it's the construction activity that defines the project. Foundation work, steel framing, historic preservation, and shoreline transformation all unfolding simultaneously.
Downtown Dallas plays a central operational role in the World Cup, despite matches being hosted at AT&T Stadium in Arlington. The downtown core is designated as a primary fan destination, media hub, and hospitality center, requiring significant upgrades to handle international crowds, broadcast demands, and security requirements. As a result, construction in 2026 is distributed across transit corridors, public spaces, and city-owned facilities. Transportation upgrades are among the most visible construction activities in 2026. DART rail stations in and around downtown Dallas are undergoing platform improvements, accessibility upgrades, and system enhancements to accommodate higher passenger volumes. Construction includes platform resurfacing, expanded queuing areas, upgraded signage, and improved vertical circulation elements such as elevators and stairs. These projects are sequenced to maintain daily transit operations while accelerating work during off-peak periods. Street-level infrastructure work intensifies in 2026. Key downtown corridors are being reconstructed or modified to improve pedestrian safety, crowd flow, and curbside operations. Construction includes widened sidewalks, improved crosswalk geometry, upgraded traffic signals, and reinforced pavement sections designed to handle buses, service vehicles, and temporary event traffic. Utility relocations accompany much of this work, requiring coordinated trenching and phased restoration. Public space upgrades represent another major component of 2026 construction. Downtown parks, plazas, and open gathering areas are being improved to serve as fan zones and event staging areas. Construction includes new hardscape surfaces, lighting systems, temporary infrastructure tie-ins, and expanded power and data capacity. These upgrades are designed to be permanent, allowing spaces to function year-round after the tournament concludes. Security-related construction advances significantly in 2026. Downtown facilities designated for World Cup operations receive perimeter hardening, controlled access points, and upgraded surveillance infrastructure. This includes installation of security bollards, reinforced barriers integrated into streetscape design, and expanded camera and monitoring networks. Much of this work is intentionally blended into public realm improvements to avoid long-term visual impact. Hospitality and event support infrastructure also sees targeted upgrades during 2026. Convention and meeting facilities in downtown Dallas undergo interior renovations to support media, operations, team logistics, and international broadcasting. Construction includes upgraded power distribution, enhanced telecommunications infrastructure, improved loading and service access, and reconfigured interior layouts to support temporary World Cup users. Wayfinding and signage infrastructure is another major focus in 2026. Crews install new directional systems designed for international visitors, incorporating multilingual signage and standardized event iconography. These systems are integrated into streets, transit stations, and public buildings, requiring coordinated installation across multiple agencies and property owners. Technology infrastructure work peaks in 2026 as well. Downtown Dallas receives expanded fiber optic capacity, upgraded wireless networks, and enhanced data redundancy to support global media transmission and high-density mobile usage. These installations often occur underground or within existing structures, making them less visible but critical to World Cup operations. From a construction sequencing perspective, 2026 is the final and most intensive year of preparation. Many projects that began in earlier years reach substantial completion during this period, while others undergo final fit-out, testing, and commissioning. The goal is to have all core infrastructure operational well before the tournament begins to allow for trial events, system testing, and security exercises. Temporary infrastructure planning also overlaps with permanent construction in 2026. Areas designated for fan festivals and live viewing require embedded connection points for temporary stages, screens, and crowd management systems. Construction teams install these features during permanent upgrades to avoid disruptive temporary installations later.
In 2026, one of San Francisco's most strategically important megaprojects under construction is taking shape across the Caltrain rail yards in the heart of central Soma. This isn't just a housing or transit upgrade. It's a massive reimagining of over 20 acres of publicly owned rail-adjacent land that has long divided the neighborhood. As construction pushes ahead this year, the rail yard redevelopment is steadily moving from planning to reality, with early phases under active build-out and long-term infrastructure elements aligning with the city's broader transit goals. Right now in 2026, the site is in the thick of foundational construction. Crews are laying the groundwork, literally, for what will eventually be a dense, mixed-use district layered above and around the working Caltrain tracks. This megaproject is part of a coordinated effort to modernize regional transportation while unlocking thousands of new homes and millions of square feet of development potential just blocks from downtown San Francisco. The Caltrain yard has been a physical and visual barrier in central Soma for generations. But in 2026, construction is actively transforming this space into an urban connector. Elevated platforms, decked structures, and street-level improvements are all in progress, designed to bridge the gap between surrounding neighborhoods and the core rail infrastructure. This year, much of the work focuses on realigning utilities, stabilizing the site for future vertical construction, and preparing parcels that will be used for new housing, office towers, and public spaces. The housing element of the rail yard redevelopment is one of the most anticipated components currently under construction. Phase 1 will deliver several hundred new residential units, with a significant portion allocated for affordable housing. These buildings, now rising on the edges of the yard, are expected to be ready for occupancy by 2028. Eventually, the full build-out will add thousands of homes to one of the city's most transit-rich locations, housing that is critically needed as San Francisco continues to face supply pressures. But housing is only one piece of this megaproject. In 2026, work is also underway on commercial development that will bring job space to the corridor, particularly targeting sectors like life sciences, tech, and creative industries. The close proximity to both downtown and future rail connections makes this site highly desirable, and the ongoing construction reflects the urgency to activate it. Several mid-rise office buildings are being framed out this year, with completion of the first wave of commercial space projected around 2029. A crucial component that's being integrated into the redevelopment in real time is transportation. The Caltrain facility itself is being reconfigured to prepare for electrification, high-speed rail integration, and potential undergrounding as part of the downtown rail extension. In 2026, while major tunneling has not yet reached the yard, planning and structural coordination are fully underway to make sure future rail service, including high-speed trains, can be accommodated. This makes the rail yard site not just a place to live and work, but a critical node in the future of statewide transit.
By the middle of the decade, one of North Texas's earliest soccer-specific stadiums is undergoing a comprehensive reconstruction that places it firmly among Dallas area megaprojects active in 2026. The new Toyota Stadium redevelopment in Frisco represents a multi-year modernization effort focused on structural capacity, revenue generation, climate mitigation, and long-term event flexibility rather than a simple renovation. Toyota Stadium originally opened in 2005, designed for a different era of Major League Soccer and a much smaller regional population. The redevelopment project restructures the existing stadium rather than replacing it, allowing FC Dallas to continue operations while construction advances in carefully sequenced phases. By 2026, the project is deep into its most technically demanding stage, with heavy construction occurring throughout the seating bowl, concourses, and building systems. Construction work during 2026 concentrates on major structural modifications. Entire sections of the lower bowl are being demolished and rebuilt to adjust rake angles, improve sightlines, and support additional vertical loads from new premium levels above. New concrete pours and steel framing are installed in phases to maintain stadium stability, while adjacent areas remain operational. This year also includes reinforcement of existing foundations to meet updated building codes and support heavier roof and canopy systems. One of the most visible construction efforts in 2026 is the installation of expanded canopy structures. These roof elements are designed to significantly increase shaded seating, addressing long-standing heat exposure issues. The canopy construction involves large-span steel trusses, integrated lighting mounts, and future-ready broadcast attachment points. Installation is staged section by section to allow partial stadium use during the soccer season. Premium seating and hospitality spaces dominate interior construction in 2026. New club lounges, lodge boxes, and suites are being built into previously underutilized stadium volume. This requires extensive mechanical and electrical upgrades, including new air handling units, upgraded power distribution rooms, and expanded data infrastructure. Plumbing systems are also being replaced or rerouted to serve higher capacity food and beverage operations. Concourse reconstruction is another major focus in 2026. Existing concourses are being widened, regraded, and reconfigured to improve circulation and accessibility. Vertical transportation systems, including elevators and stairs, are being added or relocated to comply with modern accessibility standards. These changes require careful coordination between demolition crews, concrete teams, and utility installers to avoid service disruptions. Technology infrastructure work accelerates during 2026. Crews are installing new fiber optic backbones, wireless access systems, and security networks throughout the stadium. Dedicated broadcast rooms and control spaces are under construction to support national and international television requirements. These systems are designed to accommodate future tournaments and non-soccer events without additional major retrofits. Outside the stadium bowl, 2026 construction includes the redevelopment of surrounding plazas and entry zones. Pedestrian circulation is being improved through expanded hardscape areas, upgraded lighting, and reworked security screening layouts. These exterior improvements are engineered to support higher peak attendance and year-round events, not just match days. Sustainability measures are integrated into the 2026 construction scope. Lighting systems are being converted to high-efficiency LED fixtures. Water infrastructure is upgraded with low-flow systems, and stormwater management improvements are installed to reduce runoff during heavy rain events. Older materials removed during demolition are being recycled or reused where feasible to reduce construction waste. From a timeline perspective, 2026 represents the midpoint of the redevelopment. Structural and exterior envelope work dominates early and mid-year, while interior build-outs continue into late 2026 and beyond. Some premium areas and upgraded seating sections are expected to open in phases as construction completes, allowing incremental increases in stadium functionality. Major construction activity is scheduled to continue through 2027, with final interior finishes, technology commissioning, and operational testing extending into late 2027. Full project completion is expected between late 2027 and 2028, depending on seasonal construction constraints and event scheduling. The phased delivery approach ensures continuous stadium use while transitioning the facility to its final configuration.
In 2026, one of the most visually dramatic megaprojects under construction in San Francisco is the redevelopment of the Potrero Power Station site. Rising on a stretch of industrial waterfront in the Dogpatch neighborhood, this 29-acre site is being transformed from a rusting relic of the city's energy past into a dense, mixed-use community that blends housing, innovation space, and public waterfront access. After decades of inactivity and pollution, the area is now filled with active construction, with multiple buildings rising around the preserved smokestack that once powered large parts of San Francisco. This year marks a turning point in the project's timeline. Key infrastructure has been installed, roads are taking shape, and vertical construction is advancing on several residential and commercial buildings. The first wave of occupancy is expected in 2027, while full build-out of the project will continue into the early to mid-2030s. In terms of current construction activity, 2026 is the first year where the scale and form of the new neighborhood are clearly emerging on the skyline. The development plan includes over 2,600 residential units, 20% of which are designated as affordable, along with office space, labs, retail, cultural venues, and a massive new waterfront park. In 2026, at least 4 parcels are under active construction, with cranes on site, facades being installed, and streetscape work underway to connect the site to the surrounding Dogpatch and Pier 70 developments. The power station's original brick boiler house is being stabilized and preserved to eventually be converted into a centerpiece public building, part of a broader trend in the project to mix new construction with industrial heritage. The Potrero Power Station site has long been one of the last undeveloped pieces of San Francisco's southeastern waterfront, and in 2026, it's becoming a key node in a chain of megaprojects that are physically reconnecting the city to its shoreline. The public realm is a major focus of the construction, with waterfront promenades, plazas, and parks currently being graded and landscaped to open in stages beginning in 2028. These green spaces are designed not just for beauty, but for resilience, integrated with sea level rise protection and sustainable stormwater systems. A major portion of the site is also being prepared for future commercial tenants in the life sciences and advanced technology sectors. In 2026, lab-ready office space is under construction, with leasing expected to begin the following year. These facilities are a core part of the megaproject's economic impact, offering high-tech employment opportunities and reinforcing San Francisco's role in the Bay Area Innovation Corridor. Construction in 2026 is being carried out with strict environmental oversight, given the site's legacy as a fossil fuel power plant. Soil remediation, groundwater treatment, and air quality monitoring are ongoing as each new section of the site is prepared for development. This adds complexity, but also makes the transformation more significant, turning a brownfield into a 21st century neighborhood that meets the city's housing and sustainability goals. When fully completed, the Potrero Power Station will be a dense, transit-rich waterfront extension of the city, blending over 6 acres of parks, thousands of homes, and over 1 million square feet of office and retail space into a single, cohesive community. In the landscape of San Francisco's 2026 megaprojects, it stands out for its mix of industrial past and future potential. Every structure rising here is part of a deliberate effort to reshape how cities evolve, from polluted infrastructure into vibrant, livable places.
Far south of Dallas, in Ellis County, near the city of Midlothian, the Google Data Center campus stands as one of the most infrastructure-intensive megaprojects under construction in the North Texas region in 2026. Unlike high-visibility urban developments, this project is defined by scale, power demand, and systems complexity, with construction activity focused on creating long-term digital infrastructure rather than public-facing architecture. The Midlothian Data Center is part of Google's broader expansion of hyperscale computing capacity in Texas, selected for its access to land, transmission infrastructure, and regional redundancy. The site is planned as a multi-building campus rather than a single structure, allowing phased expansion over several years. This phased approach makes 2026 a key construction year, as initial facilities transition from shell construction to systems-heavy build-out. By 2026, site-wide civil and utility infrastructure is largely established, enabling vertical construction and interior fit-out to dominate activity. Primary data hall buildings are either topped out or approaching structural completion, with reinforced concrete frames and steel roof systems designed to support heavy mechanical loads. These structures prioritize clear spans, high floor loading capacity, and modular expansion potential. Mechanical and electrical construction is the defining feature of 2026 work. Crews are installing large-scale power distribution systems, including substations, switchgear yards, and redundant electrical pathways. Multiple layers of redundancy are built into the campus, requiring parallel systems for primary and backup power. This includes integration with regional transmission lines and on-site backup generation infrastructure. Cooling infrastructure is another major focus during 2026. Data center cooling plants, including cooling towers, chillers, and water treatment systems, are under active construction. These systems are designed to handle continuous high-density server loads while optimizing water and energy efficiency. Piping networks connecting cooling plants to individual data halls are installed underground and within service corridors throughout the campus. Interior build-out of data halls accelerates in 2026. Raised floor systems or slab-integrated airflow designs are installed depending on building configuration. Server rack infrastructure, cable trays, and fire suppression systems are constructed in tightly sequenced phases. Fire protection systems typically use specialized suppression methods designed for sensitive electronic environments, requiring extensive testing and commissioning. Support buildings and ancillary facilities are also under construction in 2026. These include network operations centers, security facilities, maintenance buildings, and office space for on-site technical staff. These structures are less visually dominant, but critical for day-to-day operation and monitoring of the data center campus. Security and perimeter infrastructure advances significantly during 2026. The site includes layered physical security systems such as perimeter fencing, controlled access points, surveillance infrastructure, and secure internal zoning. Much of this construction is integrated into site grading and landscaping to maintain operational separation without excessive visual impact. Water and environmental infrastructure remains active throughout 2026. New water supply connections, storage tanks, and wastewater systems are completed or expanded to support cooling operations. Stormwater management features, including retention ponds and drainage systems, are finalized to meet regulatory requirements and protect surrounding land from runoff impacts. From a timeline perspective, 2026 represents a transition from heavy shell construction to commissioning-focused activity. While new buildings may still be under construction, several completed structures enter systems testing phases, Electrical load testing, cooling system commissioning, and network validation are conducted incrementally as each facility segment reaches readiness. Construction activity is expected to continue beyond 2026, with additional data halls and support facilities added in subsequent phases. Full campus build-out is typically planned over multiple years, allowing capacity to scale with demand. Initial operational capability is often achieved before total completion, with sections of the campus coming online independently.
In 2026, right in the heart of San Francisco's Soma district, the 5M project stands as one of the city's most active megaprojects under construction. This mixed-use development is bringing new energy and density to the blocks surrounding Mission, 5th, and Howard Streets. Long a patchwork of surface lots and low-rise structures, designed to create a live work-play ecosystem in the center of downtown. The 5M project is pushing forward this year with the final phases of its build-out, aiming for full completion by 2027. The core of the project is a multi-building, multi-acre redevelopment that includes housing, office space, community facilities, and public plazas. As of 2026, the residential component is nearing its final stages, with interiors being completed, amenity spaces outfitted, and streetscape work wrapping up. One of the tallest residential towers in the project, now visibly finished on the exterior, is expected to open its doors by early 2027, offering a mix of market rate and affordable units, over 300 in total. The office and commercial buildings that anchor the project are also active hubs of construction. Fit-outs are progressing in multiple towers, preparing space for tech, nonprofit, and creative sector tenants. In 2026, these buildings are expected to start welcoming their first occupants by the end of the year, with full occupancy likely achieved in 2027. It's part of a broader shift in the area, as Soma continues to re-establish itself not just as a tech district, but as a vibrant, mixed-use downtown core. What sets 5M apart in the landscape of San Francisco's 2026 megaprojects is its emphasis on integration with the community. More than just a real estate development, the project was designed to create active public space and cultural infrastructure. At the center of the site, the 5M Park, currently under construction, is being landscaped with flexible gathering areas, art installations, and play zones for families. This green space is scheduled to open alongside the residential buildings in mid-2027 and is expected to become a crucial urban amenity for residents, workers, and visitors alike. This year, the construction crews are focused not only on completing vertical structures, but also on activating the ground plane. Sidewalks are being widened, bike infrastructure is going in, and retail storefronts are being prepped for future cafes, shops, and local businesses. The aim in 2026 is to finish creating a neighborhood that doesn't shut down after office hours, a place where people live, work, eat, and gather 7 days a week. One of the most significant elements under construction now is the dedicated nonprofit office hub and art space, which will house multiple local organizations and creative initiatives. This facility is central to the 5M vision, supporting equity, inclusion, and community-based growth in a rapidly evolving part of the city. Completion is on track for late 2026, with programming expected to launch shortly after. From a development standpoint, the 5M project is compact compared to some of the sprawling waterfront megaprojects elsewhere in San Francisco. But in 2026, it punches far above its weight in terms of impact. Located just blocks from Powell Street BART and Muni lines, its density and transit connectivity make it a model of sustainable urban development, and its blend of housing, employment, and civic use is already influencing how other central city projects are being designed.
Set slightly apart from the historic core of downtown Dallas, The Bank of America Tower at Parkside represents one of the most prominent vertical megaprojects under construction in the Dallas region in 2026. Rising within the Park District near Clyde Warren Park, the tower is positioned as a next-generation commercial office building designed to consolidate major corporate operations while redefining the northern edge of the central business district. The project consists of a high-rise office tower with a large floor plate, advanced building systems, and integrated public realm improvements. It is designed to accommodate a single major anchor tenant while also supporting multi-tenant flexibility. The structure replaces older, lower-density development, reflecting a shift toward taller, more efficient office buildings in Dallas's core employment zones. By 2026, the Bank of America Tower at Parkside is firmly in its vertical construction phase. Structural framing dominates activity throughout the year, with reinforced concrete cores and post-tensioned floor slabs rising steadily above street level. Tower cranes remain on site through most of 2026 to support formwork, rebar placement, and concrete pours as the building progresses floor by floor. Facade installation becomes a major focus during 2026. Curtain wall systems, consisting of high-performance glass and metal panels, are installed from the lower levels upward as the structure tops out. This work is carefully sequenced with interior construction to allow mechanical and electrical rough-ins to follow closely behind the enclosure of each completed floor. The facade is engineered for solar performance, glare reduction, and long-term energy efficiency. Interior construction accelerates significantly during 2026. Mechanical, electrical, and plumbing systems are installed across multiple levels simultaneously. This includes high-capacity HVAC systems designed for dense office occupancy, advanced air filtration, and smart building controls. Electrical infrastructure includes redundant power distribution and backup systems consistent with large financial and corporate tenants. Elevator installation is another critical task, underway in 2026. High-speed elevator shafts are completed within the concrete core, followed by cab installation, guide rails, and control systems. These systems are designed to minimize wait times while serving a tall structure with large floor plates and high daily occupancy. Ground-level construction remains active throughout 2026 as well. The tower integrates structured parking, loading docks, and secure service access beneath and adjacent to the building. Streetscape improvements, including widened sidewalks, landscaping, and pedestrian connections to nearby parks and transit routes, are constructed alongside vertical progress. These elements are coordinated with city infrastructure upgrades to minimize disruption in a dense urban environment. Life safety systems are installed and tested in phases during 2026. Fireproofing, sprinkler systems, smoke control, and emergency power infrastructure are integrated as each floor reaches substantial completion. These systems must be commissioned incrementally to support ongoing construction above occupied or enclosed levels. From a scheduling perspective, 2026 represents the midpoint to late middle phase of the project timeline. Structural topping out is expected either during or shortly after 2026, depending on sequencing and weather conditions. Once the structure is complete, focus shifts more heavily toward interior finishes, tenant build-outs, and systems commissioning. Major construction activity continues into 2027, with interior finishes, lobby construction, exterior plaza completion, and final facade detailing extending well beyond the structural phase. Testing and commissioning of building systems, including elevators, HVAC, and security systems, are expected to continue through late 2027.
The Mission Rock project is one of San Francisco's headline megaprojects under active construction in 2026. Sitting directly south of Oracle Park, on what was once a windswept sea of asphalt and overflow parking lots, This 28-acre waterfront site is being turned into a dense, walkable neighborhood that combines housing, parks, offices, and retail in one of the most high-profile real estate efforts in the city. In 2026, the project is deep in Phase 1 construction. Several major buildings have already topped out, with exterior work wrapping up and interior build-outs ongoing. Full completion of this phase is expected by late 2027. When finished, it will include nearly 1,200 new residential units, over 400 of which are permanently affordable, along with 8 acres of new public space and over 200,000 square feet of office and retail space. This megaproject isn't just reshaping a site, it's helping to redefine the southern edge of San Francisco's downtown. New streets and pedestrian promenades are already being laid out, stitched together by green infrastructure and open-air plazas designed to absorb stormwater and resist sea level rise. The waterfront park, known as China Basin Park, is being built in tandem with the buildings around it. Crews in 2026 are currently sculpting the park's shoreline and planting native vegetation, with major portions set to open by 2028. Mission Rock is a public-private partnership between the San Francisco Giants and the Port of San Francisco, and the construction in 2026 reflects a long-term vision to extend the city's core outward along the waterfront. Designed as a high-density, low-emissions community, every new structure is being built to LEED Gold or higher standards. Solar panels, all-electric systems, and smart energy grids are standard here, not just features. One of the project's architectural landmarks now under construction is the Canyon, a massive mixed-use building that blends market-rate apartments with carved terraces and retail space. In 2026, the Canyon's facade is nearly complete, and interior work is progressing toward a mid-2027 delivery. Nearby, a life sciences tower being built for the biotech sector is rising quickly, with tenants expected to begin occupancy by late 2028. What makes Mission Rock such a key part of San Francisco's 2026 megaproject landscape is its fusion of uses and its central location. Unlike isolated developments on the city's edges, this project plugs directly into the transit network and urban fabric. It's within walking distance of downtown, BART, Caltrain, and multiple Muni lines. Its completion will not only provide urgently needed housing, it will expand the city's job base and public amenities in a place long dominated by underused land. As of 2026, the construction site is a hive of activity. Steel framing, glazing, mechanical installation, and hardscape development are all occurring simultaneously across multiple parcels. Each building is being developed by a different architectural team, resulting in a diversity of forms and styles that break from the monolithic look of some other megaprojects. This is intentional. Mission Rock is designed to feel like a neighborhood, not a master plan. The entire project is expected to wrap up in multiple phases through the early 2030s, with new parcels starting construction as others finish. By the time it's fully built out, Mission Rock will include 8 acres of parks, up to 1.4 million square feet of commercial space, and space for thousands of new residents.
North of Dallas, in one of the fastest-growing urban corridors in Texas, the Fields Entertainment District in Frisco is emerging as a large-scale, mixed-use mega-project that is actively under construction in 2026. The development is positioned within the broader Fields master-planned community, a multi-thousand-acre site designed to accommodate long-term population growth, corporate expansion, and regional tourism demand. The Fields Entertainment District is planned as a dense concentration of sports, hospitality, retail, dining, and public space, anchored by major destination users rather than traditional suburban commercial formats. Unlike single-purpose developments, the district is structured to operate continuously, supporting large events, daily foot traffic, and future transit-oriented growth. Its scale and phasing place it among the most consequential Dallas area megaprojects progressing through construction in 2026. By 2026, horizontal infrastructure work is largely complete, allowing vertical construction to dominate activity across the district. Roadways, utility corridors, stormwater systems, and site grading were established in earlier phases, enabling simultaneous construction of multiple buildings. In 2026, cranes, concrete crews, and steel framing operations are active across entertainment venues, hotels, parking structures, and retail blocks. One of the primary construction focuses in 2026 is vertical development of large format entertainment and event buildings. These structures require long-span steel framing, high-capacity foundations, and extensive back-of-house infrastructure. Construction includes structural steel erection, roof decking, and exterior enclosure systems designed to accommodate high occupant loads and advanced audiovisual systems. These buildings are engineered to support concerts, live events, and large public gatherings. Hospitality construction accelerates during 2026. Multiple hotel components within the district are rising simultaneously, with reinforced concrete and steel structures progressing floor by floor. Interior build-outs begin on lower levels as upper floors continue structural work. Mechanical and plumbing systems are sized for high turnover and large conference or event-driven occupancy patterns, reflecting the district's destination-oriented role. Retail and dining blocks are also under active construction in 2026. These buildings are designed with flexible floor plates to allow tenant customization while maintaining consistent architectural standards across the district. Construction includes storefront framing, exterior finishes, service corridors, and shared utility infrastructure. Emphasis is placed on pedestrian connectivity with covered walkways, plazas, and integrated outdoor seating areas built alongside vertical elements. Parking infrastructure represents a significant portion of 2026 construction activity. Multi-level parking garages are being built to serve entertainment venues, hotels, and retail uses. These structures require rapid cycle concrete construction and are designed with future adaptability in mind, allowing potential conversion or integration with autonomous or shared mobility systems later in the project's life cycle. Public realm construction expands significantly in 2026. Central gathering spaces, landscape plazas, and pedestrian spines are being formed as adjacent buildings reach enclosure stages. Hardscape installation, lighting systems, wayfinding infrastructure, and drainage features are constructed concurrently to ensure these spaces are operational as individual components of the district open. These areas are engineered to manage large crowd movements during peak events. Utility and systems integration is a major technical focus in 2026. Electrical substations, district-wide communications networks, and centralized security systems are being installed to support high-demand uses. Fiber networks are integrated throughout the district to support digital signage, ticketing systems, and event broadcasting. These systems are coordinated across multiple buildings to function as a unified operational environment. Well before the first match of the 2026 FIFA World Cup is played in North Texas, downtown Dallas is undergoing a coordinated series of infrastructure and venue upgrades that collectively form one of the region's most complex megaproject efforts active during 2026. Rather than a single construction site, the World Cup preparations consist of multiple overlapping projects focused on transportation, public space, security, mobility, and event operations, many of which reach peak construction or final delivery during 2026.
Buried beneath the surface of San Francisco's downtown in 2026 is one of the city's most consequential megaprojects under construction, the Portal, also known as the Downtown Rail Extension. This massive underground infrastructure project is finally being realized after decades of delays, aiming to connect Caltrain and eventually California's high-speed rail directly to the Salesforce Transit Center. As of this year, excavation work is ramping up, tunneling contracts are active, and the city is fully committed to completing the extension by the early 2030s. In 2026, the Portal is a hive of subterranean activity. Tunnel boring preparations are in progress, utility relocation is underway, and major downtown streets are experiencing stage disruptions as crews create access points for the underground guideways. It's one of the most complex transportation builds in the Bay Area, requiring coordination beneath some of the densest blocks in the city. Once complete, this megaproject will deliver a seamless rail connection from the peninsula and Central Valley straight into the financial core of San Francisco. The project involves building approximately 1.3 miles of new track, mostly underground, to link the existing Caltrain line near 4th and King with the Salesforce Transit Center. In 2026, the staging areas at both ends of the project are fully operational. Pile driving, shoring walls, and structural reinforcements are all happening in real time as the city begins to carve out the physical corridor that will carry thousands of passengers daily. Construction in and around Townsend, 2nd Street, and the south of Market area is active and accelerating, with visible impacts above ground and substantial progress being made below it. The Portal isn't just a rail project, it's a regional unlock. In 2026, Caltrain still terminates at 4th and King, about a mile short of downtown. That last mile has long been the missing link in Bay Area transit. By closing that gap, this project will plug regional rail directly into San Francisco's business core, reducing car dependency and reshaping how people move across the region. When complete, the Portal will allow Caltrain riders to disembark in the heart of the city and will set the stage for future high-speed rail service to run directly from Los Angeles to downtown San Francisco, without transfers. The current timeline targets a completion date in the early 2030s, with most heavy construction expected to occur between 2026 and 2030. In the context of San Francisco's other megaprojects under construction right now, the Portal stands out for its invisibility. Most of the work is happening underground, but the scale of its impact will rival that of any tower or waterfront redevelopment. Cost is high, risk is real, and coordination is intense. Crews are navigating under live utilities, major foundations, and transit lines. Every foot of tunnel requires precision, and every stage of construction must account for seismic resilience, waterproofing, and integration with existing BART and MUNI infrastructure. In 2026, engineering teams are deep into geotechnical work and soil stabilization, preparing for the eventual tunnel boring operations that will begin in earnest in 2027.
South of Dallas's central business district, the K. Bailey Hutchison Convention Center is undergoing a comprehensive expansion and reconstruction that places it among the most consequential megaprojects under construction in the city in 2026. The project is not a simple addition to the existing facility, but a phased redevelopment designed to modernize one of the largest convention centers in the region while maintaining event operations throughout construction. The expansion replaces large portions of the aging convention center with new structures that significantly increase usable exhibition space, improve circulation, and align the facility with current national convention standards. The redevelopment is also closely tied to downtown Dallas's broader urban strategy, including connectivity to surrounding districts and preparation for for major international events. By 2026, the project is in its most intensive construction phase. Demolition of outdated exhibition halls and support spaces has largely been completed, allowing new structural work to dominate the site. Crews are actively engaged in deep foundation construction, including drilled piers and mat foundations designed to support long-span exhibit halls and multi-level meeting facilities. These foundations are engineered to accommodate heavy floor loads associated with large conventions and trade shows. Superstructure construction accelerates throughout 2026. Steel framing for expansive exhibit halls is erected using long-span trusses that minimize interior columns and maximize flexible floor space. Concrete cores housing vertical circulation, mechanical shafts, and life safety systems rise concurrently. The sequencing of this work is carefully planned to allow portions of the existing convention center to remain operational while new sections are built adjacent to them. Exterior enclosure becomes a major focus during 2026. Crews install curtain wall systems, precast panels, and roofing assemblies as structural work reaches completion in phases. These systems are designed for durability, energy efficiency, and acoustic performance, reducing operational costs and improving the experience for both exhibitors and visitors. Interior construction advances rapidly in 2026 across completed structural zones. Mechanical, electrical, and plumbing systems are installed to support modern convention requirements, including high-capacity power distribution, advanced HVAC systems, and extensive data infrastructure. These systems are designed to accommodate simultaneous large events with high technology demands, such as trade shows requiring heavy electrical loads and extensive connectivity. Circulation and access improvements are a critical component of the 2026 construction scope. New concourses, meeting room clusters, and pre-function spaces are being built to improve wayfinding and reduce congestion. Vertical transportation systems, including escalators and elevators, are installed to efficiently move large crowds between exhibit levels and meeting spaces. These improvements address long-standing operational limitations of the original facility. Site and infrastructure work continues alongside vertical construction in 2026. Roadway realignments, service access improvements, and utility upgrades are underway to support increased event traffic and logistics operations. Stormwater management systems are being upgraded to meet current standards and reduce flood risk in a historically vulnerable area of downtown. From a scheduling perspective, 2026 represents a midpoint to late middle stage of the overall redevelopment timeline. Major structural elements of the new expansion are expected to be completed during this period, with enclosure and interior build-outs extending into subsequent years. Phased openings allow new sections of the convention center to come online while construction continues elsewhere on the site.
Candlestick Point and Hunters Point Shipyard are among the most active megaprojects in San Francisco as of 2026. Spanning more than 700 acres along the city's southeastern shoreline, this redevelopment effort is in full swing, reshaping two long-neglected sites into a new urban district. Construction is progressing across multiple parcels, with new streets, housing blocks, and parks taking shape, setting the stage for what will become one of the largest residential and commercial expansions in San Francisco's modern history. At Candlestick Point, where the old stadium was demolished years ago, heavy machinery is grading land for the first wave of residential and retail construction. Multiple mid-rise buildings are rising along a newly gridded street layout. These early phases, expected to complete between 2027 and 2029, will include thousands of homes, many designated as affordable, as well as the backbone of a future retail corridor and public transit connections. Parks and green infrastructure are being built alongside housing, integrating sea level rise protections and climate-resilient landscaping directly into the urban form. To the north, at Hunters Point Shipyard, development is further along. Phase 1 construction is already well underway, with completed townhomes and condos beginning to fill with residents. Additional parcels are actively under construction in 2026, adding new units monthly. Commercial spaces, artist studios, and civic buildings are also under development. Part of the project's goal to restore not just housing, but economic vitality to a part of the city long cut off from opportunity. When fully built out in the early 2030s, the combined Candlestick Hunters Point project will deliver over 12,000 new homes, more than 300 acres of open space, and millions of square feet of office, retail, and cultural uses. It's a complete neighborhood emerging from land that was, for decades, contaminated, fenced off, and largely abandoned. What's distinctive about this project in 2026 is its physical and social scale. This isn't a small infill development or a single commercial tower. It's a city-scale expansion happening within the city limits. Infrastructure is being laid from scratch. Power grids, sewer lines, transit loops, and broadband networks are all part of the foundational work occurring now. Major sections of waterfront are being rebuilt with ecological restoration in mind, with plans for habitat zones, walking trails, and public piers that will eventually reconnect residents with the shoreline. Affordable housing is a central element of the development, and 2026 marks a critical point as the first large wave of affordable units nears completion. These are being reserved in part for legacy residents of Bayview Hunters Point, addressing historic displacement and economic exclusion. Community input remains part of the planning process, particularly in shaping local hiring programs and cultural preservation efforts. Construction challenges remain. Environmental safety is closely monitored due to the site's naval and industrial history. Some parcels require more remediation than others, which is influencing the pace of development. But in terms of raw activity, cranes, crews, and square footage under construction, Candlestick Point and Hunters Point Shipyard rank among the most dynamic megaprojects in San Francisco right now.
Hidden behind its historic Beaux-Arts facade, Chicago Union Station is undergoing a long-term transformation that positions it among the city's most complex and consequential megaprojects. Rather than a single construction effort, the Union Station redevelopment is a layered program of renovations, expansions, and adjacent real estate projects designed to modernize a century-old transportation hub while it continues to serve hundreds of thousands of daily passengers. Union Station originally opened in 1925 and was designed for an era when long-distance rail travel dominated intercity transportation. Over time, train volumes declined while commuter traffic surged, leaving the station undersized for peak demand and outdated in its circulation, safety systems, and passenger amenities. By the early 21st century, deferred maintenance and congestion had become systemic problems, prompting a phased redevelopment strategy rather than a full shutdown reconstruction. Early modernization work began in the 2010s with targeted interior renovations. These included structural repairs, roof restoration, upgraded electrical and mechanical systems, and improvements to life safety infrastructure. The iconic Great Hall underwent a major restoration completed in the late 2010s, addressing water infiltration, damaged stonework, and aging lighting systems while preserving historic architectural elements. A key milestone in the redevelopment timeline was the reopening of the Chicago River entrance on the station's west side. This new access point, completed in the early 2020s, created a direct pedestrian connection between Union Station and the Riverwalk. construction required excavation, floodproofing, and the installation of new vertical circulation systems, all while maintaining rail operations below. Passenger circulation improvements have been central to the project. New corridors, widened passageways, and reconfigured waiting areas have been built incrementally to reduce bottlenecks during rush hours. These changes are designed to accommodate future ridership growth driven by increased metro service and potential intercity rail expansion. Beyond the station itself, the redevelopment includes major overbuild and adjacent construction projects that rely on Union Station's air rights. The most prominent is the Union Station Tower development on the south side of the station. Construction of this high-rise office tower began in the early 2020s and required building directly over active rail tracks. This involved the installation of massive transfer girders, vibration isolation systems, and precisely sequenced foundation work to avoid disrupting train service. Additional overbuild phases are planned for the north side of the station, with long-term proposals envisioning multiple towers constructed above rail infrastructure. These future phases remain dependent on market demand and financing, but are entitled under the broader redevelopment framework. If fully built out, the overbuild components would add millions of square feet of office and mixed-use space above one of the busiest rail terminals in the country. Transit infrastructure upgrades are another major element. Platforms and track-level systems have been incrementally improved, including drainage upgrades, platform edge repairs, and signal coordination work. These projects are often executed overnight or during limited service windows, extending timelines but allowing continuous operation. From a construction sequencing perspective, Union Station's redevelopment is uniquely constrained. All work must be phased around active Amtrak and Metra service, limiting the size of work zones and requiring extensive temporary supports. This has stretched what might otherwise be a decade-long rebuild into a multi-decade megaproject.
Some airports evolve slowly, layer by layer, molded by decades of growth. George Bush Intercontinental Airport in Houston, however, was born with a blueprint for scale from the very beginning. Constructed in the late 1960s to relieve pressure on the aging William P. Hobby Airport, IAH was never intended to be a simple regional terminal. It was a forward-looking investment, a modern answer to the booming oil economy and Houston's ascent as a global city. The site selected was expansive, a heavily forested stretch of North Houston that offered the space needed to dream big. Clearing the land was a massive undertaking on its own, requiring the removal of dense vegetation, rerouting of creeks and water flows, and the construction of entirely new utility corridors before the first runway could even be considered. Once the land was prepped, construction began with an ambitious but calculated layout. Instead of a single terminal, the airport would use a decentralized multi-terminal model, with each terminal functioning semi-independently while connected via road and eventually underground train. This modular design was intended to accommodate rapid expansion without crippling the core infrastructure. Each terminal could grow, be retrofitted, or replaced without overhauling the entire system. Early construction focused on 3 primary terminals, A, B, and C, each rising in parallel over poured concrete foundations and skeletal steel frameworks. The terminal buildings themselves were constructed with long-span trusses, allowing for wide, open concourses that minimized interior columns and maximized flexibility for airline operations. As the airport expanded, so too did its runways, crafted to handle the full spectrum of aircraft, including wide-body international jets and high-volume domestic carriers. Runway construction required extensive excavation and grading work to create a perfectly level base in Houston's famously unstable clay-heavy soil. Crews implemented multi-layered sub-base systems including geotextile membranes, to prevent cracking and heaving from the area's intense rainfall and temperature swings. Parallel runways were spaced widely enough to allow simultaneous takeoffs and landings, an operational advantage critical to IAH's future role as a hub. Throughout the 1980s and 1990s, construction never truly stopped. Terminal C was expanded into a major domestic hub for Continental Airlines, and later, Terminal E was constructed as an international gateway. The development of Terminal E marked a shift toward high-capacity, high-efficiency construction. It featured dual-level road access, streamlined customs and immigration facilities, and modern jet bridges designed for next-generation aircraft. The supporting infrastructure was just as critical. New parking structures, maintenance facilities, and de-icing pads were all built to support the increasing traffic load. Simultaneously, the airfield lighting, navigational aids, and fueling systems underwent modernization to comply with FAA regulations and future-proof the site. Beneath the terminals, the construction of the airport's people mover system added a layer of subterranean complexity. Engineers bored deep into Houston's wet subsoil to install guideways and tunnels for the train, requiring continuous dewatering, careful slope stabilization, and waterproofing membranes to prevent long-term seepage and erosion. The result was a fully automated train system that allowed passengers to move between terminals without surface traffic interference, an operational necessity in an airport spread across thousands of acres. Every phase of expansion at IOH has demanded not just engineering expertise, but logistical acumen. The airport had to remain operational throughout each construction phase, meaning crews often worked overnight or in carefully isolated zones to avoid disrupting flight schedules. Coordinating contractors, security, utilities, and aviation authorities required a master-level orchestration of timelines and contingency planning. Yet through each stage, whether laying runway concrete under humid Gulf skies or welding steel at height, Houston's flagship airport grew into a true international gateway, one poured and riveted together by sheer logistical ambition. The G Line, formerly known as the Orange Line, was never designed to stay the same. From the beginning, it was a workaround, a bus rapid transit route built in place of a rail line due to funding constraints and political compromise. But over time, its ridership and strategic location forced the city to rethink what it could be. Now the G Line is undergoing a major transformation, an infrastructure upgrade project spanning the entire 18-mile corridor through the San Fernando Valley, pushing the limits of what bus transit can do in Los Angeles. The goal is simple: increase speed, capacity, and safety. But executing that goal has required deep and complex engineering interventions at nearly every point along the route. One of the most critical changes is the installation of a state-of-the-art signal priority and preemption system. Unlike traditional traffic signals that respond to fixed timers or limited sensors, this system actively clears intersections ahead of approaching buses, reducing delays and allowing for smoother flow across dozens of street crossings. Another major element is the construction of grade separations, rail-style overpasses and underpasses, at the busiest and most delay-prone intersections. Key locations like Sepulveda Boulevard, Van Nuys, and others are being excavated and rebuilt with concrete bridges and undercrossings to allow buses to pass through without ever stopping for cross-traffic. These structures require complex retaining wall systems, traffic rerouting, and in some cases, full reconstruction of local street infrastructure around the new grades. To support higher frequency service, the corridor is being outfitted with new power systems, bus-only lanes resurfaced with heavy-duty concrete, capable of supporting constant vehicle weight and upgraded station platforms. The existing asphalt guideway, originally built to mimic light rail tracks in layout, has been deteriorating under the strain of articulated buses. Rebuilding it requires full-depth removal and replacement with reinforced concrete slabs, tied into a subsurface drainage system to prevent water intrusion and pavement shifting over time. Platform upgrades go beyond aesthetics. Stations are being lengthened to accommodate longer, higher-capacity buses and future electric models. Each platform is being raised and re-leveled to allow for near-zero gap boarding, speeding up passenger flow and improving accessibility. Integrated electrical conduits and utility vaults are also being installed during construction to prepare for future overhead charging systems as the fleet transitions to full electric. A core part of the upgrade involves upgrading the actual vehicle fleet. Metro is phasing in battery electric buses with larger passenger capacities, regenerative braking systems, and onboard diagnostics. These buses weigh more than their natural gas predecessors, which has direct implications for bridge loading, braking distances, and pavement wear. Engineers had to revisit structural tolerances across the entire corridor, from culverts and embankments to turning radii and clearance zones, to ensure long-term durability under heavier rolling stock. Fiber optic lines are also being laid alongside the corridor to support real-time monitoring. Everything from vehicle location, signal interaction, passenger load, and environmental data will be fed into Metro's central control center. This data will be used not just for dispatch, but to dynamically adjust signal cycles and reroute in case of emergencies. Drainage systems along the G line were never built for current-day storms. As part of the upgrade, culverts are being expanded, bioswales are being added to medians, and runoff channels are being lined with concrete and fitted with sensors to monitor flow levels during heavy rain. All of this is necessary to prevent trackway flooding and preserve the subgrade from erosion.
Covering more than 27 acres across multiple downtown blocks, Miami World Center is not a single construction project, but a layered mega-project built through coordinated phases that collectively reshaped the northern edge of downtown Miami. Miami World Center is located north of the Central Business District, bounded generally by Northeast 2nd Avenue, Interstate 395, and Northeast 8th Street. The site consisted for decades of underutilized parcels, surface parking, and fragmented low-rise structures. Formal planning for redevelopment began in the early 2000s, with land assembly occurring gradually over many years. The scale of the site required a master-planned approach rather than a single-build execution. Major construction activity began in the mid-2010s, following zoning approvals and infrastructure agreements with the City of Miami and Miami-Dade County. Early phases focused on horizontal construction, including demolition, mass grading, utility relocation, and the installation of new underground infrastructure. Water, sewer, power, communications, and stormwater systems were rebuilt to support millions of square feet of future development. A defining construction element of Miami World Center was its internal street grid. New public streets were carved through the site, requiring roadway construction, drainage systems, sidewalks, lighting, and streetscape elements. These streets were designed to function as permanent city infrastructure rather than private access roads, integrating the development into the surrounding urban fabric. Vertical construction followed in multiple, overlapping phases. Residential towers were among the first major structures to rise, each requiring deep foundations suited to Miami's limestone geology and high groundwater conditions. Pile foundations, reinforced concrete cores, and high-rise flat-plate floor systems were used across most towers, with construction sequenced to allow simultaneous builds on adjacent parcels. Retail and commercial structures were developed at the podium and street levels. These buildings required large-span structural systems to create flexible interior layouts for tenants. Mechanical and electrical systems were distributed through shared service corridors to reduce redundancy across the district. Loading docks and service access points were consolidated to minimize street-level disruption. One of the most significant infrastructure integrations within Miami World Center was its relationship with regional transit. The development was designed around proximity to Brightline's Miami Central Station, as well as Metro Rail, Metro Mover, and bus connections. Pedestrian corridors and public spaces were constructed to funnel foot traffic between transit nodes and interior blocks, requiring careful grading and structural decking over below-grade utilities. Construction timelines varied by parcel. Early residential and retail components began delivering units around 2018 and 2019. Additional towers and commercial buildings were completed in the early 2020s, with construction continuing in phases as market conditions and financing allowed. Unlike a single mega project with a fixed end date, Miami World Center evolved through staggered completions. Hotel construction formed another major component. Large hospitality structures required distinct structural and mechanical systems, including back-of-house service cores, conference spaces, and rooftop amenities. These buildings were constructed concurrently with residential towers, increasing logistical complexity across the site. Parking infrastructure was largely integrated into podiums and below-grade levels. This required excavation, dewatering, and reinforced slab construction beneath active building sites. Parking systems were designed to serve multiple uses, including residential, retail, and event traffic, reducing the need for standalone garages. From a construction management perspective, Miami World Center required coordination across dozens of contractors, architects, and engineers. Crane operations, concrete pours, and material deliveries were scheduled to avoid conflicts within a dense, active site. Safety planning was critical due to the proximity of Interstate 395 and ongoing city traffic. The megaproject also included public space construction, such as plazas and pedestrian promenades. These areas required structural support for landscaping, irrigation systems, and integrated lighting. Public realm construction often occurred late in each phase, following heavy structural work. Rising high on the Ethiopian plateau, more than 2 kilometers above sea level, Addis Ababa has always been a city of layers: old and new, formal and informal, chaotic and alive. But over the past few years, the city has begun to take on an entirely new shape. The Addis Ababa City Corridor and Smart City Project is the centerpiece of that transformation, a sweeping plan to modernize the capital, expand its infrastructure, and create a blueprint for what a 21st century African metropolis can look like. At its heart, the project is about connection. Addis Ababa has grown rapidly, with millions of people moving in from rural regions, but the city's layout and infrastructure never quite kept pace. Roads became crowded, neighborhoods expanded without clear planning, and public services struggled to keep up. The City Corridor Plan aims to tie it all together, a network of modern boulevards, transit routes, and green corridors stretching across the city, designed to integrate housing, commerce, and technology in one continuous urban system. Think of it as both a transportation project and a digital backbone, built to link everything from the city's financial district to its emerging industrial zones. The smart city component is what makes it truly forward-looking. It's not just about widening roads or adding new buildings. It's about embedding intelligence into the fabric of the city itself. Sensor-based traffic management, integrated public data systems, and sustainable utilities that can monitor and adapt in real time. Streetlights powered by solar panels, automated waste collection, water systems that track usage and detect leaks, and transport routes that update dynamically based on congestion. All of these features form part of the vision. Addis Ababa isn't just being expanded, it's being reprogrammed. Alongside the technology, there's also a strong architectural and social vision. The new city corridors are planned to include dedicated pedestrian paths, landscaped parks, and mixed-use developments that bring homes, offices, and public spaces together. Rather than separating zones by function, the aim is to create integrated communities that reduce the need for long commutes and support more sustainable living. It's a response to the sprawl that has defined much of the city's past growth, turning what used to be dusty, disconnected suburbs into modern, connected districts. The construction itself is happening in phases, with local and international teams working together to upgrade transport corridors, build smart infrastructure, and prepare new land for development. It's a massive logistical challenge involving coordination between ministries, tech companies, and city planners, all while trying to minimize disruption in one of Africa's busiest urban centers. But despite the complexity, progress continues steadily, with visible changes appearing year by year. New roads lined with smart lighting, new districts emerging with coordinated urban layouts, and data centers forming the digital core of the city's new systems. What makes the Addis Ababa City Corridor project stand out isn't just its scale, but its symbolism. Ethiopia is positioning itself as a regional leader in technology and infrastructure, and the capital city is its proving ground. The project represents a shift from reactive urban growth to proactive, technology-driven design, an attempt to future-proof a city that's expected to keep growing for decades to come. And when it's complete, Addis Ababa could stand as one of the first truly smart cities on the African continent, built not just to handle its population, but to evolve intelligently alongside it. Just east of Chicago's traditional downtown core, an entire neighborhood has been constructed almost from nothing, making Lakeshore East one of the most significant urban megaprojects in the city's modern history. Built on former rail yards and surface parking lots, the development represents a long-term effort to extend the loop eastward while reconnecting downtown to Lake Michigan. The Lakeshore East site covers roughly 28 acres, bounded by Randolph Street, Lakeshore Drive, and the Chicago River. For much of the 20th century, the land was dominated by Illinois Central Rail infrastructure, service roads, and vacant parcels created by transportation realignments. Large-scale redevelopment became possible only after the decline of rail use and the consolidation of downtown planning efforts in the late 20th century. Formal planning for Lakeshore East began in the 1990s, with a master plan approved to guide phased construction over multiple decades. The development was designed as a high-density, mixed-use neighborhood composed primarily of residential towers supported by retail, office space, hotels, and public amenities. Infrastructure construction was a foundational requirement, including new streets, utility corridors, and a central park system built above active, underground roadways and service structures. One of the defining construction achievements of Lakeshore East is its multi-level design. Much of the neighborhood is built atop a podium that conceals lower-level roads, loading areas, and mechanical systems. This required extensive structural engineering, including reinforced concrete decks capable of supporting high-rise towers while allowing traffic and service access below. At the heart of the project is Lakeshore East Park, a 5-acre landscaped public space completed in the mid-2000s. The park was constructed early in the development timeline to establish a residential anchor and improve land value for surrounding parcels. It includes terraced lawns, water features, and pedestrian paths, all built over underground infrastructure. Vertical construction began in the early 2000s and progressed in phases. Early towers included high-rise residential buildings such as the Lancaster, the Chandler, and the Regatta, which helped establish the neighbourhood's residential character. Subsequent phases introduced taller and more architecturally ambitious towers as market demand increased. One of the most prominent structures in Lakeshore East is the Aqua Tower, completed in 2009. Its mixed-use program includes residential units, hotel rooms, and retail space. The tower's construction required complex formwork and balcony systems due to its non-repetitive floor plate design. Aqua became a visual landmark and signaled the neighborhood's arrival as a major component of Chicago's skyline. Other major towers followed, including the Blue Cross Blue Shield Tower, completed in the late 2000s, which added significant office space to the area. This building required integration with existing lower-level infrastructure and direct connections to surrounding streets and transit access points. Residential construction continued through the 2010s with towers such as Coast, Tides, Cascade, and Vista. Vista, completed in the early 2020s, is one of the tallest residential buildings in the world and marked the near completion of the neighborhood's original master plan. Its construction involved deep foundations, high-strength concrete, and extended crane operations due to its height and proximity to Lakeshore Drive. From a timeline perspective, Lakeshore East has been under active construction for more than 2 decades. While the majority of major towers are now complete, the development is not entirely finished. Remaining parcels are reserved for future buildings, and incremental construction is expected to continue into the late 2020s as market conditions allow.
Sometimes, the ground beneath a project tells its own story. For Suvarnabhumi Airport, that story began in the wetlands east of Bangkok, a flood-prone expanse known as Nong Neu Hau, or Cobra Swamp. Turning that swamp into the busiest aviation gateway in Thailand required not just engineering, but imagination on an almost mythic scale. Before the first beam could be raised, the land had to be tamed. Crews moved in with heavy machinery to carry out one of the most extensive ground stabilization efforts ever undertaken in Southeast Asia. The saturated, unstable soil demanded deep foundations, and tens of thousands of concrete piles were driven deep into the ground to support the immense weight of the terminal and its associated infrastructure. This foundational work took years, but it was critical. It was the invisible backbone that would allow the entire project to stand. As soon as the earth was secured, the race to construct the terminal complex began. At the center of the airport's design was the main passenger terminal, a behemoth of steel and glass that, when completed, ranked among the largest in the world under a single continuous roof. The architecture, sleek, curving, and inspired by Thai aesthetics, was as much an engineering feat as it was a visual statement. Erecting its monumental roof structure required custom fabricated trusses and steel arches, assembled on site with millimeter-level precision. These components weren't just massive, they were complex, with each one shaped to accommodate the terminal's signature wave-like profile. Teams worked in coordinated shifts around the clock, craning sections into place, welding, securing, and enclosing vast sections of the structure in a construction ballet that had to hit precise deadlines despite Bangkok's oppressive heat and monsoon rains. Logistically, the site was a challenge. Located more than 25 kilometers from the city center, every piece of equipment, every shipment of materials, had to be routed through carefully orchestrated supply chains. Specialized components, including miles of glass paneling and advanced HVAC systems, were brought in from around the world and integrated into a site that was changing daily. The baggage handling system alone required its own sub-project, spanning multiple levels and kilometers of track, sensors, and software. Even beneath the polished floors and soaring ceilings, the airport's skeleton was a dense network of mechanical systems, each one installed during a phase of construction that had to proceed without disrupting others. While much of the international spotlight shone on the passenger terminal, the runways were no less impressive. Constructed with precision, the dual runways were laid with reinforced concrete to handle heavy aircraft movements, and their drainage systems were meticulously engineered to mitigate the flood risks of the region. Massive underground water management channels and pumping systems were embedded throughout the airport's footprint, ensuring operational continuity even during Thailand's intense rainy season. Control towers, fire stations, maintenance hangars, all of it had to rise in synchronization, each piece playing a critical role in the final orchestration. In the final stretch of construction, coordination became paramount. Hundreds of contractors, thousands of workers, and dozens of subcontracted firms had to bring their work together into a seamless whole. Testing and commissioning were conducted on an enormous scale. Fire suppression systems, electrical grids, telecommunications, lighting, signage, all had to function flawlessly before a single flight could depart. And despite political upheavals and public scrutiny, the airport opened to commercial service with a sense of scale and ambition that left little doubt. This wasn't just a new airport. It was a milestone in Thailand's infrastructure history.
Long before Miami's skyline signaled its rise as a global city, the expansion of Port Miami and its tunnel interchanges quietly re-engineered the region's economic foundation through one of the most consequential infrastructure megaprojects in the county's history. Port Miami, located on Dodge Island in Biscayne Bay, underwent a coordinated expansion program during the late 2000s and early 2010s, aimed at transforming the port into a post-Panamax global trade hub. This effort combined portside construction, navigational improvements, and highway-grade tunnel interchanges into a single integrated mega-project. The goal was to remove physical, maritime, and logistical constraints that limited cargo growth while separating freight movement from downtown Miami's surface streets. One of the earliest and most critical construction components was the deepening of the port's main navigation channel. Prior to expansion, the channel depth restricted access for larger container vessels. Dredging operations began in the early 2010s and involved removing millions of cubic yards of material from Biscayne Bay to achieve a depth of approximately 50 to 52 feet. This work was completed in 2015, timed to coincide with the expanded Panama Canal, allowing Port Miami to receive fully loaded post-Panamax container ships for the first time. On NAS, Dodge Island itself, extensive terminal reconstruction took place in parallel with dredging. Older cargo berths were demolished and rebuilt with reinforced concrete wharves capable of supporting heavier cranes and higher container loads. New gantry cranes, some of the largest in the world at the time of installation, were erected on reinforced rail systems embedded into the key structure. Yard areas were regraded and paved to accommodate automated container handling equipment and higher stacking densities. Utility infrastructure beneath the port was also rebuilt. This included new electrical substations, stormwater drainage systems, fuel distribution lines, and communications networks designed to support modern terminal operations. These upgrades were completed incrementally to avoid disrupting ongoing cargo and cruise activity, requiring phased construction zones across the island. The landside component of the expansion centered on the Port of Miami Tunnel and its highway interchanges, which together form the port's primary freight access system. Construction of the tunnel began in 2010 and was coordinated directly with port expansion schedules. The tunnel consists of two submerged roadway tubes connecting Dodge Island to Watson Island, bypassing downtown Miami entirely. Equally significant were the tunnel interchanges themselves. On the mainland side, major roadway reconstruction was required to tie the tunnel directly into Interstate 395 and Interstate 95. This involved building new elevated ramps, retaining walls, and transition structures capable of handling heavy truck volumes at highway speeds. Existing roadways were demolished and realigned, with traffic maintained throughout construction using temporary detours and phased lane shifts. On the port side, Dodge Island underwent extensive reconfiguration to integrate tunnel portals with internal port circulation. New access roads were built, grade separations installed, and security checkpoints relocated to streamline truck movement. These changes allowed cargo vehicles to enter and exit the port without crossing cruise passenger traffic, significantly improving operational efficiency and safety. The tunnel excavation itself was completed in 2013, but the interchange construction and systems integration extended into 2014. The full tunnel and interchange system opened to traffic in August 2014, marking a major milestone in the port expansion timeline. From that point forward, thousands of trucks per day were rerouted away from downtown Miami streets and directly onto the interstate network. The expansion program also included rail infrastructure improvements. Port Miami's on-dock rail connection was rehabilitated and reactivated, linking the port directly to Florida East Coast railway lines. Track upgrades, switching yards, and loading areas were constructed to enable intermodal freight transfer, reducing dependence on trucking for long-haul cargo movement. In the context of Miami's biggest megaprojects, the Port Miami expansion and tunnel interchanges differ from high-rise developments by operating as a systems-level transformation. The project did not create a single landmark structure, but instead rebuilt the physical processes that allow the city to function as a logistics hub. Its completion aligned with other regional megaprojects, including airport cargo expansion and downtown redevelopment, forming an interconnected infrastructure network. Down on the shores of the Red Sea, where the old port city of Jeddah stretches out between desert and water, two enormous projects are quietly redrawing the map: Jeddah Central and Jeddah Economic City. Together, they represent a vision of transformation unlike anything the city has seen before, turning this historic gateway into a modern global hub for business, culture, and tourism. What makes these developments remarkable isn't just their scale, but the way they weave old and new, ambition and heritage, into something that feels distinctly Saudi, yet unmistakably international. Jeddah Central sits right in the heart of the city, taking over more than 5 square kilometers of waterfront that once housed the old desalination plant and underused industrial land. It's being reinvented as a new downtown, built around a sweeping marina and a waterfront district lined with cultural landmarks, residential towers, and entertainment spaces. The master plan revolves around 4 main landmarks: a sports stadium, an oceanarium, an opera house, and a museum, all designed to anchor Jeddah's identity as a cultural and leisure destination. Around them will rise luxury hotels, office towers, parks, and promenades, all connected by shaded walkways and open public spaces, meant to bring life back to the seafront. But this isn't just about aesthetics. The project's layout is designed around sustainability and smart urbanism, integrating renewable energy, green transport systems, and water recycling technologies suited to the coastal climate. It's a major shift for Jeddah, which has long struggled with congestion and uneven urban growth. The plan envisions a livable, walkable downtown that balances modernity with comfort, turning the Red Sea coast into a showcase for the new Saudi lifestyle that's emerging under the country's Vision 2030 framework. The idea is to create not just buildings, but experiences, places where art, commerce, and everyday life blend seamlessly. A short distance to the north, Jeddah Economic City takes that ambition and scales it up to a global level. This is the site of the Jeddah Tower. The skyscraper that aims to surpass 1 kilometer in height and become the tallest building in the world. The tower is the centerpiece of a vast mixed-use development covering more than 50 square kilometers, designed to serve as a new economic hub for trade, finance, and innovation. When complete, Jeddah Economic City will have residential neighborhoods, educational institutions, business districts, and green open spaces all linked together by advanced infrastructure and digital systems. The city's design places a strong focus on integration with the wider region. Ports, highways, and logistics corridors will tie it directly into the national network that connects Jeddah to Makkah, Medina, and eventually Neom, farther north. In many ways, Jeddah Economic City represents the country's broader push to diversify its economy beyond oil, creating new industries that can attract global investment and talent. Taken together, Jeddah Central and Jeddah Economic City show two faces of Saudi Arabia's urban transformation. One is cultural and civic, centered on lifestyle and heritage. The other is economic and technological, reaching for the future through engineering and ambition. Both are shaping a new identity for Jeddah, a city that once served as the gateway for pilgrims, now evolving into a gateway for ideas, enterprise, and modern urban life along the edge of the Red Sea. Beneath Chicago's streets, rivers, and neighborhoods lies one of the largest underground civil engineering systems ever built, a megaproject whose scale rivals any visible skyscraper or transit expansion in the city. The Tunnel and Reservoir Plan, commonly known as TARP or the Chicago Deep Tunnel, is a decades-long infrastructure program designed to control flooding, reduce sewer overflows, and protect regional waterways. The origins of TARP trace back to the mid-20th century when rapid urban growth combined stormwater and sewage into a single system that frequently overwhelmed treatment plants. Heavy rainfall routinely forced untreated wastewater into the Chicago River system and Lake Michigan. Planning for a permanent solution began in the 1960s, with construction formally launching in 1975 under the oversight of the Metropolitan Water Reclamation District of Greater Chicago. The core of the project consists of more than 100 miles of deep rock tunnels excavated between 150 and 300 feet below ground. These tunnels range from 9 to over 30 feet in diameter and were bored through solid dolomite bedrock using tunnel boring machines customized for long-duration, high-pressure excavation. Construction occurred in phases over several decades, with tunneling largely completed by the early 2000s. The tunnels function as massive underground storage conduits. During storms, combined sewage is diverted from surface sewers into the deep tunnel network, preventing street flooding and uncontrolled discharges into waterways. Once storms pass, the stored water is gradually pumped to treatment plants for processing. This operational strategy required the construction of dozens of drop shafts, some wider than 30 feet, and extending hundreds of feet downward, connecting surface infrastructure to the tunnel system. A second major component of TARP is its reservoir system, which represents the most visible and recent phase of construction. These reservoirs were designed to provide additional storage capacity beyond the tunnels. The largest of these is the Thornton Composite Reservoir, built within a former limestone quarry south of the city. Construction began in the late 1990s, with phased completion allowing partial operation before the full reservoir was finished. When fully complete, Thornton provides over 7 billion gallons of storage, making it one of the largest stormwater reservoirs in the world. Additional reservoirs include the McCook Reservoir in western Cook County. This facility has been constructed in stages, with the first phase becoming operational in the late 2010s. Full completion, including its second major stage, is scheduled for the mid-2020s. Once finished, McCook will add approximately 10 billion gallons of combined stormwater and sewage storage capacity to the system, significantly increasing flood protection for large portions of Chicago and surrounding suburbs. Along a former industrial corridor stretching between Lincoln Park and Bucktown, one of Chicago's most ambitious redevelopment megaprojects has been planned on land that sat underutilized for decades. Lincoln Yards is a proposed large-scale, mixed-use development intended to transform roughly 53 acres along the North Branch of the Chicago River into a new urban district, combining residential, commercial, infrastructure, and public space construction. The site historically housed steel mills, manufacturing plants, and later, large-scale storage and light industrial uses. Much of the land required extensive environmental remediation due to contamination from its industrial past. Preparatory work over the past several years has focused on soil cleanup, demolition of remaining industrial structures, and riverbank stabilization, which represent the earliest construction-related activities tied to the project.
Amid the swirling dust and sun-baked plains of northern Egypt, where the echoes of antiquity still hum beneath the surface, a different kind of monument began to rise in the 20th century. Not one, carved from stone, but cast in concrete and steel. Cairo International Airport was conceived as Egypt's primary portal to the modern world, a replacement for the aging Al Mazah Airport that could handle the soaring demands of commercial aviation in a capital rapidly expanding in population, influence, and ambition. From its inception, the project was steeped in logistical complexity, shaped by the challenges of working in a desert environment while tethered to the ambitions of a globalizing era. The early phases of construction focused on establishing the core infrastructure that would serve as the foundation for decades of layered growth. Located northeast of central Cairo, the site had to be fully excavated, graded, and serviced with basic utilities in an area that, at the time, lacked deep infrastructure. Massive swaths of earth were moved, and early work involved laying vast concrete aprons and taxiways capable of withstanding the punishing heat and seasonal extremes of the region. The soil conditions, arid and loosely compacted, required specialized engineering techniques to ensure long-term stability. Foundations were reinforced with deep footings and treated aggregate layers to mitigate shifting and cracking under the relentless Egyptian sun. Terminal construction began with a modular approach, an intentional strategy designed to facilitate future expansion without disrupting operations. Terminal 1, known in its early form as the Old Airport, was built with broad, open-plan halls supported by a reinforced concrete frame and long-span steel beams. The design prioritized resilience over aesthetics, focusing on airflow, structural simplicity, and load-bearing efficiency. Glass curtain walls and shading systems were introduced to reduce thermal gain while still allowing for natural light, crucial in a location where daytime temperatures often soared. As aviation volumes increased, the terminal underwent multiple expansion campaigns, each requiring retrofitting older structures with newer systems for baggage handling, ventilation, and fire safety, all while keeping the terminal partially operational. The addition of Terminals 2 and 3 marked a significant evolution in construction philosophy. Terminal 2, originally completed decades ago, eventually underwent a complete overhaul to bring it in line with international standards. This reconstruction was a feat of surgical engineering. The original frame was selectively demolished, and new sections were grafted into the existing structure. Contractors worked in tight, active zones, reinforcing aging concrete, integrating new seismic protections, and threading miles of electrical, plumbing, and HVAC lines through spaces never designed to hold them. Terminal 3, on the other hand, was a clean slate. constructed from the ground up as a state-of-the-art facility to accommodate wide-body aircraft and higher passenger volumes. Its frame was built from high-strength concrete and a steel roof truss system, supporting a terminal footprint that included dual-level departure and arrival flows, jet bridge systems, and a matrix of automated luggage belts built into a multi-tiered substructure. Beyond the terminals, Cairo's runways demanded careful engineering. Laid in parallel orientations to optimize wind handling and maximize simultaneous movements, the runways were constructed with high-durability concrete overlays and embedded lighting systems for all-weather operations. Groundwork involved excavation and subgrade stabilization across thousands of linear meters, requiring constant calibration to maintain level grading and load-bearing integrity. Runway expansions had to be synchronized with radar installations, air traffic control upgrades, and expanded taxiway systems to manage growing traffic without compromising safety or efficiency. Meanwhile, auxiliary construction, parking decks, maintenance hangars, fuel farms, and cargo facilities developed in parallel. Each support system required its own logistical plan, from fuel pipeline installations and fire suppression systems to cold storage zones for cargo handling. The cumulative effect was a sprawling, highly compartmentalized aviation complex whose every square meter had to be engineered for durability, redundancy, and heat resilience.
Beneath Biscayne Bay, hidden from the skyline that defines Miami's megaproject boom, the Port of Miami Tunnel represents one of the most complex and consequential infrastructure projects ever built in South Florida. The Port of Miami Tunnel was designed to directly connect Dodge Island, home to Port Miami, with the interstate highway system, creating a dedicated underground freight corridor between the port and Interstate 395 and Interstate 95. Before the tunnel, cargo trucks were forced to move through downtown Miami streets, creating chronic congestion, safety issues, and delays that constrained the port's growth. The tunnel fundamentally restructured how goods move through the city, making it a critical component of Miami's broader megaproject transformation. Planning for the tunnel began decades before construction, with serious development efforts accelerating in the early 2000s as Port Miami expanded into a major global cargo and cruise hub. Construction officially began in 2010, after years of environmental review, financing negotiations, and engineering studies. The project was delivered through a public-private partnership, an uncommon approach at the time for U.S. transportation megaprojects, involving the Florida Department of Transportation and a private concessionaire responsible for design, construction, financing, and long-term operation. The construction scope centered on two parallel tunnel tubes, each approximately 3,900 feet long, bored beneath Biscayne Bay. The tunnels were excavated using a massive tunnel boring machine specifically designed to operate in Miami's challenging geology, which consists of porous limestone, sand, and a high water table. The tunnel boring machine, weighing thousands of tons, was launched from Watson Island and advanced underwater toward Dodge Island, cutting through bedrock while simultaneously installing precast concrete liner segments to stabilize the tunnel walls. Excavation operations required continuous groundwater management and precise pressure control to prevent collapse or water intrusion. The tunnel alignment passed beneath active shipping channels, requiring careful coordination to avoid disrupting port operations and marine traffic. Spoil material removed during tunneling was transported and processed without interfering with surrounding urban and maritime infrastructure. In addition to the underwater tunnels, the project included extensive cut and cover construction on both ends. On Watson Island and Dodge Island, large access portals were excavated, requiring dewatering systems, retaining walls, and deep foundations to support the tunnel entrances. New roadway interchanges were built to connect the tunnel directly to I-395, eliminating truck traffic through surface streets in downtown Miami. Construction also included advanced ventilation buildings, fire suppression systems, emergency cross passages between tunnel tubes, and real-time monitoring systems. These safety features were essential to meet federal highway tunnel standards and ensure continuous operation in a hurricane-prone region. The tunnel was engineered to withstand storm surge, seismic forces, and long-term exposure to saltwater conditions. The project faced multiple technical and schedule challenges during construction. Delays occurred due to mechanical issues with the tunnel boring machine, groundwater infiltration events, and the complexity of working beneath an active port and bay. Despite these challenges, tunneling was completed in 2013, marking one of the most technically demanding phases of the project. Following structural completion, several years were dedicated to roadway finishing, systems installation, testing and commissioning, ventilation, lighting, traffic control, and emergency systems underwent extensive testing before the tunnel was open to traffic. The Port of Miami Tunnel officially opened in August 2014, completing a construction timeline of roughly 4 years. Within the context of Miami's biggest mega projects, the Port of Miami Tunnel stands apart from high-rise developments like Panorama Tower or Brickell City Centre. Rather than reshaping the skyline, it reshaped the city's logistical foundation. By removing thousands of trucks per day from downtown streets, the tunnel enabled parallel megaprojects in residential, commercial, and cultural development to proceed without freight congestion, limiting growth. In the vast emptiness of northwestern Saudi Arabia, where desert and mountains stretch endlessly under the sun, a line of glass and steel is being drawn across the landscape. A city unlike any that has ever been built before. It's called The Line, and it forms the central vision of NEOM, a futuristic megaproject meant to redefine what urban living can be in the 21st century. The idea sounds almost impossible at first, a city that isn't sprawling outward, but extending straight for hundreds of kilometers, only 200 meters wide, yet home to millions of people. But that's exactly the scale of ambition Saudi Arabia is pursuing, nothing less than the reinvention of civilization itself. The concept behind The Line begins with simplicity. Instead of spreading a city outward in all directions, it compresses everything into a single linear corridor that runs through desert valleys and over coastal plains. The two mirrored walls of the city rise more than 400 meters, enclosing a narrow interior where people will live, work, and travel vertically rather than horizontally. The structure is designed to function as a continuous vertical metropolis, where everything, from housing and offices to schools, parks, and public transit, is stacked efficiently inside a climate-controlled environment. At its core, the line is meant to operate without cars, roads, or traditional streets. Instead, it relies on a high-speed underground transport system that can move people from end to end in minutes. The idea is that every daily need, groceries, healthcare, education, recreation, should be within a 5-minute walk. By eliminating cars and long commutes, the designers aim to create a city where time is reclaimed for people, where nature and urban life coexist without one overwhelming the other. Sustainability sits at the center of the entire plan. The line is being built to run entirely on renewable energy, primarily from solar and wind power, and its compact footprint minimizes land use and environmental impact. The vertical design allows the surrounding desert and mountains to remain untouched, preserving natural ecosystems while housing millions of people in a fraction of the space that a normal city would require. The structure's mirrored facade isn't just aesthetic. It reflects sunlight to reduce heat absorption and helps control the city's internal temperature. Engineering something of this magnitude pushes the boundaries of what's physically possible. The foundation requires precision construction over uneven terrain, and the structural demands of building two continuous walls, hundreds of meters high, across such distances are immense. The integration of transportation systems, data networks, energy grids, and vertical living spaces has to function seamlessly for the vision to work. Every part of the city will be monitored and managed through AI-driven systems, adjusting lighting, temperature, and logistics dynamically to optimize efficiency and comfort. The line also represents a broader idea about the future of Saudi Arabia. It's not just a mega project, it's a statement of national transformation. It reflects the country's drive to diversify beyond oil, to attract technology, investment, and global talent, and to present itself as a center of innovation. For the government, the line is both an economic experiment and a symbol of ambition, projecting the image of a nation willing to take risks to shape the next century. Whether it succeeds or not, the line is already changing the conversation about what cities can be. It's forcing engineers, architects, and planners around the world to imagine new forms of living, new ways of organizing society, and new relationships between humans and the environment. In the middle of the desert, a city that runs in a straight line may seem improbable, but that's precisely the point. It's a bet on imagination and on the belief that the future doesn't have to look anything like the past. South of Chicago's Loop and directly east of Grant Park, one of the most ambitious and complex megaprojects ever proposed in the city is planned not on open land, but above active rail infrastructure. One Central Chicago is a large-scale, long-term development proposal centered on constructing a massive transit-oriented platform over the Metra Electric Rail Yard near Soldier Field, redefining how Chicago approaches air rights development. The core of the One Central proposal is the construction of a multi-level structural deck spanning more than 30 acres of rail lines. This deck would serve as the foundation for an entirely new neighborhood, allowing vertical development to rise above existing transportation corridors without displacing them. The engineering challenge is central to the project, requiring heavy load-bearing caissons, vibration isolation systems, and phased construction that allows uninterrupted rail operations below. The project is structured around a new central transit hub, envisioned as one of the largest in the Midwest. The hub would integrate Metra electric trains, CTA bus services, potential future rail connections, and pedestrian and bicycle networks into a single, consolidated station. Transit infrastructure is planned as the first major construction phase, establishing the structural deck and station facilities before any private buildings rise above. One Central is approved conceptually as a multi-decade development, not a single construction effort. The full build-out is projected to extend into the 2040s, with individual phases dependent on financing, tenant demand, and infrastructure funding. Early construction would focus on the deck, transit facilities, and utility systems, a process expected to take several years before vertical development begins. The proposed scale places One Central among the largest megaprojects in Chicago history. At full build-out, the plan allows for millions of square feet of mixed-use development, including residential towers, office space, hotels, academic and research facilities, and cultural venues. Building heights would vary across phases, with some towers reaching high-rise and super-tall classifications, though final designs remain flexible. Infrastructure construction is the defining feature of the project. Beyond the deck itself, One Central requires new roadways, stormwater management systems, electrical substations, and telecommunications networks. Because the site sits between Lake Michigan and downtown, flood resilience and drainage engineering are critical components of the design. Elevated building pads and integrated water management systems are planned to address long-term climate risks. Unlike many Chicago megaprojects, One Central has not yet entered full construction. As of the mid-2020s, the project remains in advanced planning and approval stages, with negotiations focused on public-private partnerships, transit funding, and long-term governance. The project's viability is closely tied to securing funding for the transit hub, which is considered essential to unlocking the value of the surrounding development. The location gives the project strategic importance. It sits between the museum campus, McCormick Place, Soldier Field, and downtown, creating a potential bridge between Chicago's civic core and its convention and entertainment districts. The development would also reconnect neighborhoods long separated by rail infrastructure, using the deck as both a building platform and a public realm. From a construction sequencing standpoint, One Central differs from traditional real estate projects. No single building can proceed independently. Each phase depends on completion of shared structural and transit elements, making coordination and long-term scheduling central to the project's execution. This complexity places One Central closer to infrastructure megaprojects like transit expansions than conventional mixed-use developments.
They didn't just build an airport on the shores of the Black Sea. They carved a new future for a nation out of rock, sea, and ambition. The construction of Istanbul Airport, one of the most audacious infrastructure projects of the 21st century, was not just a matter of civil engineering. It was a national statement, a vision chiseled into existence with relentless speed and almost cinematic scale. From the very first shovel of Earth, this project wasn't designed to follow global aviation standards. It was meant to redefine them. The site itself was a challenge from the start. A mix of former open-pit coal mines, wetlands, and unstable terrain that required millions of cubic meters of earth to be moved, compacted, and stabilized. This wasn't just land reclamation, it was land transformation on a continental scale. Thousands of workers labored around the clock, building not only runways and terminals, but the very ground those structures would stand on. The scale of the terminal alone is staggering. Designed to be the largest under a single roof anywhere on Earth, the main passenger terminal covers over 1 million square meters. Its skeleton is steel, its skin glass and aluminum, but its foundation is poured from unflinching confidence. Every beam, every column was part of a choreography measured in millimeters, but executed at megastructure scale. Construction teams sourced materials from all over Turkey and beyond, fueling a logistical operation that mirrored military precision. Concrete was poured by the ton, and cranes moved like clock hands over the site, some of them among the tallest and most powerful in the world. And at the heart of it all, the project had to maintain momentum in a political and economic climate that was, at times, deeply volatile. Timing was everything. The goal was clear from the start. Open fast, open big. Unlike projects that slowly build up capacity, Istanbul Airport was envisioned to make a splash from day one. That meant building not one, but multiple parallel runways right from the outset, designed to handle hundreds of flights a day with minimal delay. The air traffic control tower, with its sleek tulip-inspired silhouette, was one of the first structures to rise, signaling the pace and design sophistication the rest of the site would follow. Around it, a spiderweb of service roads, utility tunnels, fuel lines, and drainage systems had to be laid out with unerring accuracy. Every inch of the infrastructure was future-proofed to accommodate the long-term goal. Over 200 million passengers annually once all phases are complete. No corner of this site was spared from overachievement. The cargo facilities were built to rival dedicated freight airports, with massive warehouses and high-speed loading systems constructed at breakneck pace. The runway system, built across 4 phases, was designed not only for volume but for wind, direction optimization, weather resilience, and operational efficiency that could outpace even the world's most established airports. Drainage was a particular challenge, given the area's geography. Massive culverts and underground reservoirs were constructed to manage rainwater and prevent flooding, a vital concern in a place where the sea is never far and the weather can turn swiftly. Even power and data lines were installed with redundancy and scalability in mind, buried deep and routed through protected channels to safeguard against both overload and sabotage. When construction crews finally handed over the keys, what they left behind wasn't just an airport. It was a piece of infrastructure that looked less like a public utility and more like a declaration carved into the earth. The sheer act of building it, under such tight deadlines, across such difficult terrain, and on such a colossal scale, stands as one of the great modern feats of engineering. It's not just what was built, it's how it was done. Quickly, relentlessly, and without blinking in the face of impossible complexity. Tucked just south of downtown Los Angeles, Exposition Park has always been a place of ambition, home to world-class museums, the LA Memorial Coliseum, and the beating heart of the city's cultural and sporting life. But what's unfolding there now isn't just an upgrade, it's a full-scale transformation, timed to align with the arrival of the 2028 Olympic Games. This is the Exposition Park expansion, and it's one of the most concentrated, multi-layered megaprojects happening anywhere in the city. We're talking about more than 100 acres of dense, high-profile development, the kind of space where architecture, infrastructure, landscape, and engineering have to work in seamless coordination, and every inch of it is being reimagined, stitched together into a new kind of urban park, one that blends Olympic-scale sports facilities with civic space, transit access, and cultural presence. At the center of this expansion is the Lucas Museum of Narrative Art, an enormous, fluid, almost spaceship-like structure that defies traditional design logic. Spanning over 300,000 square feet, the building floats above the landscape on concrete pylons, allowing for an uninterrupted park to run beneath it. Engineering that vision into reality meant solving a long list of structural challenges. The museum's form curves and bends with few right angles, requiring a steel skeleton unlike any conventional grid. Every beam had to be custom fabricated. Load paths had to be recalculated from scratch. But that's only one piece. Adjacent to it, new Olympic training facilities are being added in and around the Coliseum, including athlete, housing, high-performance sports labs, and temporary structures built to IOC standards. These aren't off-the-shelf projects. Each facility must meet international competition criteria while being adaptable for post-Games public use. That means flexible infrastructure, modular designs that can expand or collapse depending on future needs, and utility corridors capable of serving both a global broadcast event and a local youth sports league. A new mobility hub is also under construction, tightly integrated with the K Line, Crenshaw LAX Line, regional bus service, and pedestrian corridors linking USC, the Natural History Museum, and BMO Stadium. This isn't just about moving people, it's about rethinking access. Engineers are embedding smart traffic systems, ADA upgrades, secure bike lanes, and crowd flow modeling to handle Olympic-scale surges without overwhelming local streets. Then there's the landscape itself. More than 14 acres of new green space are being carved into the existing grid, with bioswales, permeable pavement, and stormwater recycling systems hidden beneath sculpted terrain. Everything is dual purpose. That shaded plaza? It's also an emergency egress route. That rolling hill. It's backfilled over a utilities corridor with seismic isolation joints. Every tree and trail was designed not just for beauty, but for function, cooling microclimates, guiding crowds, and managing runoff during rare but intense LA storms. Beneath the surface, the engineering complexity continues. Utility upgrades, electric, water, fiber, gas, are being laid out like a circulatory system for a future-proof urban core. Crews had to dig and trench with surgical accuracy, often working just inches away from existing structures that couldn't be moved or shut down. Phasing the construction without interrupting events at the Coliseum or the Museum District meant round-the-clock scheduling, heavy prefabrication, and just-in-time delivery logistics.
Set within the dense fabric of downtown Miami, Miami Central represents one of the most complex, privately delivered megaprojects ever completed in the city, combining rail infrastructure, vertical construction, and urban redevelopment into a single coordinated build. Miami Central is a mixed-use, transit-oriented development centered on the southern terminus of Brightline's intercity rail system. The project occupies multiple city blocks between Northwest 1st Avenue and Northwest 6th Street, directly adjacent to Government Center. Planning for Miami Central began in the early 2010s as part of a broader effort to reintroduce intercity passenger rail to Florida, while simultaneously redeveloping underutilized downtown land. Construction officially began around 2014, with early work focused on site preparation, demolition of existing low-rise structures, utility relocation, and rail corridor reconstruction. The project required rebuilding active rail alignments while maintaining freight operations on the Florida East Coast Railway, necessitating phased construction sequencing and temporary track realignments. At the core of Miami Central is the Brightline station, constructed as an elevated rail terminal spanning multiple blocks. The station structure required long-span concrete and steel framing to support train platforms above street level while allowing uninterrupted traffic flow beneath. Platform construction included high-load track slabs, vibration mitigation systems, signaling infrastructure, and integrated safety systems compliant with federal rail standards. Below and around the station, the project incorporated significant structural podium construction. Large transfer slabs were built to distribute loads from residential towers above while accommodating open concourses, retail space, and passenger circulation areas below. This approach allowed rail, pedestrian, and vehicular systems to coexist within a constrained urban footprint. Miami Central includes multiple high-rise towers developed in phases. The first residential towers began vertical construction after the station structure was well underway. These towers required deep foundations and auger-cast piles to manage Miami's soil conditions and groundwater levels. Structural systems used reinforced concrete cores with flat plate floor construction, optimized for residential occupancy and high-rise efficiency. In addition to residential units, Miami Central incorporated office space, hotel components, and retail frontage. Mechanical, electrical, and plumbing systems were designed to operate independently across uses while sharing centralized infrastructure where possible. Loading docks, service corridors, and back-of-house systems were embedded into the lower levels to minimize surface disruption. A defining construction challenge was integrating multiple transportation modes into a single site. Miami Central connects Brightline Intercity Rail, Metro Rail, Metro Mover, Metro Bus, and pedestrian networks. Construction included new elevated walkways, platform connections, fare control zones, and vertical circulation systems, linking existing transit infrastructure to newly built spaces. Roadway reconstruction was another major component. Portions of Northwest 1st Avenue and surrounding streets were rebuilt to accommodate new traffic patterns, curbside loading, and pedestrian access. Streetscape improvements included drainage upgrades, structural decking over rail corridors, and reinforced pavement designed for heavy service vehicles. The timeline of Miami Central unfolded in stages. Rail corridor and station construction progressed between roughly 2014 and 2017. The Brightline station reached functional completion in late 2017, coinciding with the launch of passenger service between Miami and Fort Lauderdale, later extended to West Palm Beach. Full station operations began in early 2018. Residential towers were delivered in phases, with initial buildings completed around 2018 and additional towers finishing in subsequent years. Retail and public spaces opened gradually as tenant build-outs were completed. The project did not conclude with a single completion date, but by the late 2010s, Miami Central was fully operational as a transit hub and mixed-use district. Within the context of Miami's biggest megaprojects, Miami Central stands out for being privately financed and rail-centric. Unlike publicly led infrastructure efforts such as the Port of Miami Tunnel or airport expansions, Miami Central combined transportation infrastructure with real estate development under a single master plan. This approach shifted how large-scale projects could be delivered in Miami's urban core. From a construction management perspective, Miami Central required coordination among rail engineers, vertical construction contractors, transit agencies, and city departments. Work occurred simultaneously above, below, and alongside active transit lines, requiring constant monitoring of settlement, vibration, and structural movement. On Chicago's South Branch of the Chicago River, a new sports and urban development mega project is being proposed that would add a purpose-built soccer stadium to the city's expanding list of large-scale construction efforts. The new Chicago Fire Stadium, planned as part of the broader The 78 development, represents a significant shift in how professional soccer infrastructure is integrated into Chicago's urban core. The project centers on the construction of a soccer-specific stadium for Chicago Fire FC, designed to replace the club's current use of Soldier Field. The proposed stadium would seat approximately 22,000 to 25,000 spectators, aligning with modern Major League Soccer standards that prioritize compact design, fan proximity to the field, and operational efficiency. The stadium is planned to be fully enclosed on all sides, with a roof structure intended to improve acoustics and weather protection while maintaining open sight lines to the surrounding cityscape. The site is located on a long vacant 62-acre parcel south of Roosevelt Road, historically used as rail yards and industrial land. This area has been undergoing years of environmental remediation and infrastructure planning. The stadium would occupy a portion of the land designated for entertainment and civic uses within the 78 master plan, a larger mixed-use mega project that includes residential towers, office buildings, research facilities, and riverfront public space. Construction for the stadium has not yet begun, but the proposal outlines a privately financed project, primarily funded by the team's ownership group. Estimated costs range in the hundreds of millions of dollars, reflecting not only the stadium itself, but also associated infrastructure such as utility connections, riverwalk improvements, and transit access enhancements. The intent is to minimize direct public subsidy while leveraging existing city investments already committed to the 78's foundational infrastructure. From a construction standpoint, the stadium would involve deep foundation work due to the site's industrial past and proximity to the river. Soil stabilization, pile driving, and flood mitigation measures would be required before vertical construction could begin. The building structure is expected to combine reinforced concrete lower levels with a steel superstructure supporting seating tiers and roof elements. Prefabrication is likely to be used for seating bowls and roof components to reduce on-site construction time. Timeline projections place the earliest possible start of major construction in the mid to late 2020s, contingent on final approvals, design completion, and coordination with adjacent developments. If approved on an accelerated schedule, construction would likely take approximately 2 to 3 years, suggesting a potential opening near the end of the decade. This would align the stadium's debut with later phases of the 78's build-out, rather than its initial residential and office towers. The stadium's integration into Chicago's transportation network is a key planning component. The site is within walking distance of existing CTA rail lines and metro services, and future transit enhancements tied to the 78 could further improve access. Pedestrian bridges, expanded sidewalks, and riverwalk connections are anticipated as part of the surrounding public realm improvements, allowing the stadium to function as a year-round anchor rather than a single-use venue. From an urban planning perspective, the project marks a departure from the city's previous approach to large sports facilities. Instead of placing the stadium on the urban periphery or adapting an existing multi-purpose venue, this mega project embeds a professional sports facility directly into a dense, mixed-use district. This allows stadium operations to support nearby businesses, housing, and public spaces, extending economic activity beyond match days. The proposed stadium also addresses long-standing operational challenges for Chicago Fire FC. Soldier Field's size, configuration, and scheduling constraints have limited matchday atmosphere and revenue potential. A dedicated stadium would provide full control over scheduling, sponsorship integration, and fan experience, while also reducing operational costs associated with renting a large NFL venue.
Where the Port of Los Angeles meets the open Pacific, a vast transformation is underway. Once a place defined by rusted cranes and abandoned warehouses, San Pedro's historic waterfront is being reimagined as a massive public destination. This is West Harbor, a $500 million redevelopment project that's reshaping 42 acres of prime harborfront land into one of the largest and most ambitious waterfront revitalizations in California history. For decades, the San Pedro waterfront was a place of industry. Cargo ships, rail lines, and container yards dominated the landscape, cutting the community off from its own shoreline. The ocean was always there, visible but unreachable. The idea behind West Harbor was radical in its simplicity. Take land that had long been the realm of cranes and commerce and return it to the people. Replace the shipping yards with open promenades. Tear down the fences, open the gates. But turning a gritty, industrial port into a modern, urban waterfront park isn't just a matter of cosmetics. It's an enormous engineering challenge. Beneath the surface, the ground itself needed rebuilding. Years of marine traffic, heavy equipment, and salt exposure had weakened bulkheads and corroded old pilings. Before a single restaurant could open, crews had to stabilize the soil, drive hundreds of deep foundation supports, and upgrade the harbor's edge to withstand both tidal surges and seismic shocks. At the heart of the project is a massive promenade that wraps along the water, designed not just for pedestrians, but for resilience. The concrete pathways are elevated to anticipate sea level rise, with drainage systems engineered to handle storm surges from both land and ocean. New docks are being constructed to support visiting ships and harbor cruises, each one designed with floating gangways that rise and fall with the tides, maintaining access even in extreme conditions. West Harbor isn't just infrastructure, it's experience. The development includes over 150,000 square feet of space for retail, dining, and entertainment, with anchor tenants ranging from artisan markets to major restaurants. A 6,200-seat outdoor amphitheater is being built directly on the waterfront, engineered to deliver concert-quality acoustics in a coastal environment, where sound bounces unpredictably off water and wind. Engineers had to design the stage foundation to accommodate both musical events and the occasional pounding from Pacific storms, using vibration damping, materials, and reinforced steel substructures. All of this, performance spaces, restaurants, shops, sits on land reclaimed from decades of industrial use. That meant a full environmental remediation process, involving soil testing, removal of contaminated fill, and installation of modern stormwater systems to prevent runoff from polluting the bay. A particularly complex element was integrating the new West Harbor seamlessly with the surrounding transportation network. This meant widening roads, building new intersections, and coordinating with nearby freight operations, all while preserving the historic landmarks that give San Pedro its identity. The historic battleship Iowa, docked nearby, had to be factored into every phase of design, ensuring visitor access remained open during construction. The engineering teams also had to work in parallel with the Port of LA's ongoing operations, scheduling pile driving and crane activity to avoid disrupting maritime logistics. Even as the heavy machinery rolls and concrete is poured, the bigger vision is already taking shape. This isn't just about leisure. It's about reconnecting a city with its coastline. For generations, San Pedro's waterfront was a wall of industry. West Harbor turns it into a front porch.
In the quiet countryside of southern France, surrounded by pine forests and rolling hills, there's a construction site unlike any other on Earth. It's not another dam or bridge or skyscraper. It's a machine built to recreate the power of the sun. This is ITER, the International Thermonuclear Experimental Reactor, and it represents one of the most ambitious scientific collaborations in human history. The goal here is nothing short of mastering nuclear fusion, the same reaction that fuels stars, and turning it into a practical source of energy for our planet. The concept sounds simple in theory, but has pushed the limits of engineering for decades. Fusion happens when two light atomic nuclei, usually forms of hydrogen called deuterium and tritium, collide at extremely high temperatures and fuse into helium, releasing enormous amounts of energy. The problem is that replicating those conditions on Earth means creating and controlling plasma that's hotter than the core of the sun, about 150 million degrees Celsius, and keeping it stable long enough to extract useful power from it. That's where ITER comes in. At the heart of the project is the tokamak, a donut-shaped reactor designed to contain the plasma using magnetic fields so powerful they could lift aircraft carriers. The machine itself is a masterpiece of precision. Its vacuum vessel weighs over 5,000 tons. Its superconducting magnets are cooled to near absolute zero, and every component must align with millimeter accuracy, despite being the size of a small building. The idea is that when the system is fully operational, the reactor will produce 10 times more energy than it consumes, something no fusion experiment has ever achieved before. What makes ITER truly remarkable is how global it is. It's being built through a partnership of 35 nations, including the European Union, China, the United States, Russia, Japan, India, and South Korea. Each partner contributes different components, from cryogenic systems to magnet coils to diagnostic sensors, and all of them have to fit together perfectly when assembled in France. Coordinating that kind of international supply chain is an engineering feat in itself, with massive pieces of hardware shipped across oceans and transported by custom-built convoys that crawl through rural roads to reach the site. The scale of the infrastructure around the tokamak is equally astonishing. There's a massive cryoplant to cool the magnets, a system of vacuum pumps, cooling water loops, radio frequency heating systems, and an entire electrical network dedicated to feeding the experiment's colossal appetite for power. When ITER begins its first plasma runs, it will consume more electricity than a medium-sized city, though the aim is to prove that fusion can eventually produce far more energy than it uses. Yet the challenge isn't just technical, it's also philosophical. Fusion has been called the energy of the future for over half a century, and ITER's success or failure could finally determine whether that future is real. If it works, it could open the door to commercial reactors that generate clean, virtually limitless energy from seawater, with no carbon emissions and almost no radioactive waste. But for now, ITER remains an experiment, a monument to human cooperation and scientific persistence, standing quietly in Provence as thousands of engineers and scientists work to capture the power of the stars here on Earth. Chicago's position as a global transportation hub is being reinforced through one of the largest aviation infrastructure programs ever undertaken in the United States: the long-term modernization of O'Hare International Airport. This mega project stands as a central pillar among Chicago's largest construction efforts, reshaping air travel capacity, terminal design, and airfield performance for decades to come. The current modernization effort builds on earlier construction phases that began in the mid-2000s. The foundational work was the O'Hare Modernization Program, initiated in 2005, which focused almost entirely on the airfield itself. Prior to this program, O'Hare relied on intersecting runways that caused cascading delays during bad weather. Over a 16-year construction period, the airport added 4 new runways, extended 2 existing ones, and permanently closed several older runways. This reconfiguration created a parallel runway system, increasing hourly aircraft capacity and reducing delays by tens of thousands of flights annually. The final runway opened in late 2020, marking the operational completion of that phase by 2021. With the airfield rebuilt, Chicago shifted focus to the terminal complex through a new initiative known as O'Hare 21. This phase represents the most visible portion of the mega project and is currently underway. At the center of O'Hare 21 is the O'Hare Global Terminal, a new international terminal replacing the existing Terminal 2. Construction planning began in the late 2010s, with early site work and enabling projects starting in the early 2020s. Full-scale construction is expected to progress throughout the decade, with the terminal targeted for completion around 2030. The global terminal will fundamentally change passenger flow at O'Hare. It is designed to consolidate domestic and international arrivals in one location, eliminating the need for long transfers between terminals. The building will span more than 2 million square feet and include expanded customs processing, upgraded security screening, and redesigned concourses built to handle larger wide-body aircraft. Terminal 2 will be demolished in phases as the new structure is completed, allowing airport operations to continue throughout construction. Beyond the main terminal, the modernization includes 2 new satellite concourses located west of the existing terminal core. These concourses are critical capacity expansions and are being built in parallel with the global terminal. Satellite 1 is further along in planning and early construction, with utility relocation, foundation preparation, and tunnel alignments already established. Satellite 2 is scheduled for later phases, dependent on airline demand growth. Both satellites will be connected to the main terminal via underground pedestrian tunnels and an automated people mover system. Together, they are expected to add dozens of new gates, many capable of handling international flights. Supporting infrastructure is a major part of the mega project. New baggage handling systems are being installed to support higher passenger volumes and reduce transfer times between flights. Electrical substations, stormwater systems, and communications infrastructure are being upgraded or rebuilt to meet modern performance and resilience standards. These elements are largely invisible to passengers, but represent a substantial portion of construction cost and complexity. The project timeline extends into the early 2030s. While individual components, like satellite concourses, may open earlier, the full terminal area plan is expected to be substantially complete around 2032. Construction sequencing is designed to avoid disrupting daily operations at one of the busiest airports in the world, requiring extensive temporary facilities and phased demolition.
There are airports that simply connect cities. And then there's Denver International, an airport that feels more like a myth, wrapped in fog, conspiracy, and raw, undeniable scale. Set against the jagged silhouette of the Colorado Rockies, DN isn't just an air hub, it's a riddle in concrete, steel, and prairie wind. From the moment you approach, you realize this place is different. The terminal roof rises like a row of white peaks, a canvas of fabric stretched into spires that mimic the mountains beyond. It's both architectural poetry and functional design, a nod to the natural world in the middle of a high-tech frontier. But behind the beauty lies a beast of logistics and ambition. Denver International is the second largest airport in the world by land area. Spanning over 50 square miles, it's larger than Manhattan. That space isn't just empty fields, it's a calculated investment in the future. Room to grow. Room to reimagine what an airport can be. When DEN opened in 1995, it did so after delays, budget overruns, and more than a little controversy. It replaced the old Stapleton Airport, not because Denver needed a slightly better facility, but because it needed to think bigger, radically bigger. At the time, few could have predicted how essential that gamble would become. Today, with air traffic climbing and cities swelling, that oversized footprint now looks like foresight. Operationally, it's a marvel. The runways, 6 in total, are set wide apart, allowing simultaneous takeoffs and landings in nearly any weather. This efficiency is crucial in Denver's unpredictable climate, where snowstorms can whip in with little warning. Beneath the surface, a vast tunnel system once built for an ambitious, but famously flawed, automated baggage system still snakes its way below ground. A reminder of how pushing boundaries doesn't always go smoothly. Yet what truly sets Denver apart isn't just the infrastructure, it's the atmosphere. This airport breathes mystery. From strange murals to the giant blue horse sculpture at the entrance, complete with glowing red eyes, DEN has become a magnet for conspiracy theories and urban legends. Secret bunkers, underground facilities, coded art. It's all part of the lore. Whether you believe any of it or not, there's no denying the airport has a presence. But look past the shadows, and you'll see something else. A living symbol of Denver's evolution. The airport isn't just a pit stop between coasts. It's a launchpad into the American West. It connects the Rockies to the world, fuels the city's economic engine, and anchors Colorado's global reach. And it does all of that with an eye on what comes next. DEN is currently in the midst of multi-billion-dollar expansions, new gates, modernized terminals, and advanced security systems. It's shedding some of its 90s skin and stepping boldly into the 21st century. But even as it transforms, that original ambition, that sense of scale and audacity, still lingers in the wide-open airfields and endless walkways. Brightline West isn't an idea, it's under construction. A $12 billion high-speed rail megaproject designed to link Los Angeles to Las Vegas in just over 2 hours, cutting a trip that often takes over 5 by car. With speeds reaching 200 miles per hour and over 260 miles of new rail corridor, this is one of the largest and most complex infrastructure projects ever attempted in the American Southwest. The alignment runs primarily along the I-15 corridor, chosen for its straight path, existing right-of-way, and the massive volume of traffic it sees. Over 50 million people travel between LA and Las Vegas each year, many of them stuck in stop-and-go congestion. Building next to a major interstate, however, comes with logistical and engineering demands on a different scale. Crews must work within narrow margins between freeway traffic and construction zones, requiring extensive concrete barriers, temporary detours, and phased sequencing to avoid bottlenecks. The trains will operate entirely on dedicated, grade-separated track. That means no level crossings, no signal delays, and no sharing with freight or commuter rail, making Brightline West a true high-speed rail system by global standards. To achieve this, over 300 structures are being constructed along the route, including overpasses, bridges, wildlife crossings, and viaducts. Every one of them is engineered to withstand extreme desert heat, high wind speeds, and seismic loads consistent with California building codes. One of the most technically demanding sections involves crossing the Kaijan Pass, an elevation climb of over 3,000 feet between the Inland Empire and the high desert. This stretch requires extensive cut-and-fill operations, retaining walls and reinforced embankments. Specialized track design, including banked curves and controlled gradients, ensures that trains maintain high speeds without overstressing the vehicles or the infrastructure. Trackbed construction is another layer of complexity. Unlike conventional rail, high-speed systems require exacting tolerances for smoothness and alignment. The subgrade must be compacted and stabilized to millimeter-level accuracy, followed by multiple layers of ballast, reinforced concrete slab track, and vibration-damping materials. These systems are monitored in real time through embedded sensors, allowing for predictive maintenance and immediate response to deviations. Powering the system is an electrified catenary line running the full length of the corridor. This requires constructing hundreds of miles of new transmission infrastructure, including substations, overhead gantries, and high-voltage feeds. To ensure uninterrupted service, the power supply is designed with built-in redundancy and real-time switching capabilities. Utility coordination across 2 states and multiple counties adds further layers of complexity to every mile built. The train sets themselves, based on Siemens Velaro or similar European high-speed rail platforms, will be custom modified for American standards. Each unit will feature aerodynamic nose cones, regenerative braking systems, crash energy management structures, and lightweight aluminum bodies to reduce axle load and track wear. These aren't commuter trains. They're precision-built machines designed to run at 200 mph across open terrain, with acceleration, deceleration, and safety systems modeled after Japan's Shinkansen and Germany's ICE.
Rather than rising from untouched land, the new Miami-Dade airport emerged through one of the largest continuous airport reconstruction programs ever undertaken in the United States, transforming Miami International Airport into what is effectively a rebuilt megastructure operating in real time. Miami International Airport sits west of downtown Miami and functions as the primary global aviation gateway for South Florida and Latin America. By the late 1990s, the airport's original mid-20th century terminals, roadways, and airfield systems were no longer capable of handling projected passenger growth, new aircraft sizes, or modern security requirements. Miami-Dade County responded by launching a long-term capital improvement effort, commonly referred to as the airport's New Airport Program, a reconstruction on the scale of a greenfield build while maintaining daily operations. The centerpiece of this transformation was the North Terminal Development Program, a multi-billion-dollar mega project that replaced large portions of the airport's aging infrastructure. Planning began in the late 1990s, with construction starting in the early 2000s. The program consolidated multiple older concourses into a single, linear terminal complex designed to improve passenger flow, security processing, and aircraft operations. Construction involved complete demolition of outdated concourses, utility corridors, and support buildings, followed by new foundations, structural frames, and terminal shells built adjacent to active runways and taxiways. This required phased construction sequencing to keep aircraft movements uninterrupted. New terminal structures were built using long-span steel and reinforced concrete systems capable of supporting large wide-body aircraft gates and high passenger volumes. The North Terminal was developed in multiple phases. Early phases focused on airside infrastructure, including new taxi lanes, aircraft parking aprons, and fuel hydrant systems. Subsequent phases delivered passenger processing spaces, including ticketing halls, security checkpoints, baggage handling systems, and customs facilities. The first major sections opened to passengers in the mid-2000s, with full substantial completion achieved in the early 2010s. A critical component of the new airport construction was the installation of an automated people mover system connecting the terminal to remote rental car facilities and parking structures. This required elevated guideways, stations integrated into terminal buildings, and control systems installed above active roadways. The people mover significantly reconfigured landside access to the airport. The reconstruction extended beyond terminals. Miami-Dade County invested heavily in runway rehabilitation and expansion, including pavement reconstruction, lighting upgrades, and drainage improvements. Taxiway geometry was modified to accommodate larger aircraft, such as the Airbus A380 and Boeing 777. These airfield works were completed incrementally over many years, often overnight, to avoid disrupting flight schedules. Cargo infrastructure was also rebuilt as part of the airport's Megaproject evolution. New cargo buildings, cold storage facilities, and access roads were constructed to support Miami's role as a major freight hub for perishable goods. These upgrades aligned with parallel megaprojects at Port Miami, reinforcing the county's logistics network. Security and resilience upgrades formed another major construction layer. Post-9/11 requirements led to reinforced terminal layouts, expanded security screening zones, and hardened building systems. Mechanical, electrical, and plumbing systems were replaced or upgraded to modern standards, including redundant power supplies and advanced fire protection. Flood mitigation and drainage improvements were incorporated to address Miami's climate and storm exposure. The timeline of the new Miami-Dade Airport build spans more than a decade. Major construction activity peaked between roughly 2004 and 2012, with continuous smaller projects extending beyond that period. By the early 2010s, the airport had effectively transitioned from a mid-century facility into a modern aviation megastructure, capable of handling tens of millions of passengers annually. Within the broader context of Miami's biggest megaprojects, the airport reconstruction stands alongside developments such as the Port of Miami Tunnel, Brickell City Center, and large-scale transit investments. Unlike vertical megaprojects, the airport rebuild was horizontal and systemic, requiring coordination across aviation operations, federal agencies, contractors, and airlines. If you've ever traveled through Britain by train, you know the experience can be both scenic and slow, with Victorian-era infrastructure still carrying millions of passengers every day. That's exactly what the HS2 project set out to change, a high-speed rail line designed to reshape how the country moves, connecting London with the Midlands and the North at speeds the UK has never seen before. It was imagined as the backbone of a new, modern transport network, one that could rival continental Europe's fast and efficient trains while easing the pressure on the country's crowded existing lines. High Speed 2, or HS2, is being built in stages. The first phase stretches from London to Birmingham, cutting travel times almost in half. The second was originally meant to continue north toward Manchester and Leeds, linking major cities with sleek new trains running at over 320 kilometers per hour. The ambition wasn't just about shaving minutes off journeys, it was about balancing Britain's economic geography, pulling growth and investment away from the capital and spreading it toward regions that had long been left behind. In theory, faster travel meant stronger regional economies, easier business connections, and new job opportunities across the country. But building HS2 has been anything but straightforward. It's one of the largest infrastructure projects in Europe, involving hundreds of kilometres of tunnels, viaducts, and embankments carved through some of England's most densely populated areas. The sheer complexity of the route required boring machines to tunnel under London suburbs, elevating tracks across countryside landscapes, and even designing specially built wildlife bridges to protect local ecosystems. Every section of the project is a microcosm of engineering challenges: soft clay, urban congestion, ancient infrastructure, and a constant balancing act between speed, safety, and sustainability. The construction workforce alone numbers in the tens of thousands, operating across dozens of sites at once. Giant tunnel boring machines, each named and tracked like ships, have been chewing their way through chalk and clay beneath the Chiltern Hills, creating vast underground passageways for the new line. Elsewhere, massive viaducts rise over river valleys, and new depots and stations take shape in cities that have been waiting decades for this kind of modernisation. Euston and Old Oak Common in London are being transformed into vast transport hubs, designed not just for HS2, but to connect seamlessly with existing networks, integrating the old with the new. However, despite its technical brilliance, HS2 has faced intense criticism and political turmoil. Costs have soared far beyond initial estimates, delays have stacked up, and parts of the northern extensions have been scaled back or cancelled entirely, leading many to question whether the project can still deliver on its original promises. Environmental groups have voiced concerns about the loss of woodland and natural habitats, while others argue that the benefits to the broader economy still justify the disruption. Even so, what remains of HS2 still represents a massive leap forward for Britain's rail system. When the first trains begin running between London and Birmingham, they'll mark the country's entry into true high-speed travel, a mode that much of the world has already embraced. And while the vision may have shrunk from its earliest days, the project still stands as a symbol of long-term ambition, the kind of investment that tries to build not just for today's commuters, but for generations yet to come.